What if, on the very night humanity stood ready to witness a messenger from beyond the stars, the lights inside America's premier space agency suddenly went out? Not by sabotage, not by cosmic disaster, but by the grinding gears of politics. Imagine the silence. Observatories armed, orbiters aligned, instruments humming in anticipation, and then, as the clock struck midnight, NASA's voice was cut off. This is not a movie trailer. This is the real tension of September 2024, when a government funding deadlock plunged the United States into a shutdown. NASA, bound by law, halted public communication just as 3I divided by Atlas, the third confirmed interstellar object ever detected, slid into a rare observational window near Mars. The overlap was so unnerving that even the most rational minds could not help but feel a shiver. For more than half a century, NASA has been the trusted narrator of our cosmic journey. Apollo's first steps, Voyager's pale blue dot, Hubble's visions of nebulae, these were not just scientific milestones, they were shared human moments, stories etched into our collective memory. NASA does not merely gather data, it translates that data into meaning, into a sense of where we fit in the grand theatre of the cosmos. So when that voice falls silent, especially at a moment of extraordinary significance, the void it leaves is deafening. And what a moment it was. 3I divided by Atlas is not another familiar comet from the Oort cloud, looping predictably around the Sunday. It is a trespasser, a visitor forged in another star's nursery, travelling unbound through interstellar darkness for millions of years before glancing at our solar system. We had seen 2 before Oumuamua in 2017, its shape and trajectory baffling astronomers, and 2I divided by Borisov in 2019, glowing like a textbook comet yet still alien in composition. But this third object arrived with timing and geometry that could have offered something unprecedented. The possibility of close-range observation from the fleet of orbiters stationed at Mars. Never before had humanity been so equipped to greet such a traveller. Mars orbiters with high-resolution cameras, telescopes armed with adaptive optics. Supercomputers are primed to detect the faintest anomalies in their light curve. For the first time, we could have peeled back layers of mystery in real time, asking whether these interstellar guests behave like comets, whether their chemistry carries clues of distant stellar nurseries, even whether their shapes or motions defy our neat categories. The stage was set, the instruments were ready, the questions were sharp, and then came the shutdown. NASA websites froze, stamped with a blunt notice. Due to the lapse in government funding, this website is not being updated. NASA TV broadcasts stopped. Social media channels went silent. Scientists, furloughed, were legally forbidden to share updates with the public. The spacecraft kept working, yes. The orbiters kept recording, but the bridge between observation and public awareness was severed. The information pipeline, the very lifeline that turns raw telemetry into shared human wonder, was cut. Picture the absurdity. A spacecraft circling Mars may have been capturing faint glimmers of an object from another star, data that could redefine our understanding of interstellar matter. Yet back on Earth, the agency responsible for telling that story was muzzled by congressional gridlock. Americans, and the world, were left staring at a blank feed at the exact moment a cosmic visitor swept by. The instruments did not stop. The silence was not in space, it was in Washington. That coincidence alone would be strange. But layered atop years of rising public mistrust in institutions, it felt conspiratorial. After all, coincidences are easy to rationalize. Governments shut down, celestial bodies move on their own timetable. But what are the odds that our third ever interstellar visitor, a once-in-history chance for close observation, would coincide with enforced institutional silence? To a rational analyst, it is a bureaucratic clash of calendars. To the emotional human heart, it is a narrative too sharp, too cinematic, to ignore. The mind splits in 2 directions. On one hand, reassurance. The data is safe. It will be processed later. NASA has no reason to conceal it. On the other hand, suspicion. Why now? Why silence at the precise hour when the world should have been watching? That duality, the cold comfort of logic against the hot pulse of unease, is what makes September 2024 unforgettable. It reminds us not just of the fragility of institutions, but of the delicate thread by which human wonder hangs. When that thread is cut, even temporarily, the questions multiply. And so the story begins with silence. A silence created not by cosmic distance, but by human politics. A silence that fell at the very moment when the universe itself decided to speak. When a government shuts down, it is not just a budgetary squabble in the halls of Congress. It is a chain reaction. Agencies deemed non-essential shut their doors. Thousands of federal workers are sent home. Research halts. Outreach disappears. And for NASA, the consequences are uniquely dramatic. Unlike some agencies that operate quietly behind the scenes, NASA is a public-facing storyteller. Its discoveries are meant to inspire, to update, to broadcast in real time. During a shutdown, that entire public voice is silenced. By law, NASA is restricted under the Anti-Deficiency Act. Unless a function is directly tied to human safety or the protection of government property, it must stop. That means astronauts on the International Space Station remain supported. Mission-critical spacecraft keep running, but the communication pipeline, the act of sharing discoveries with the world, grinds to a halt. Engineers still monitor spacecraft health. Scientists may still receive raw telemetry in secure servers, but the public sees nothing. No fresh images on websites, no breaking news on social media, no analysis from the mission teams. A total blackout, even as the instruments continue recording. Now, imagine the timing. In late September 2024, negotiations in Washington collapsed. Funding expired. The government shut down. NASA's communication staff was furloughed. And at the very same moment, 3I divided by Atlas began its passage into the Mars observational window. For professional astronomers, the overlap was maddening. For the public, it was haunting. In an era when suspicion thrives, silence becomes its own form of evidence. Consider how the scene looked to a person scrolling through their phone on September 30th. For weeks, the headlines had built anticipation. Interstellar object approaching Mars. Experts had gone on television, podcasts, and YouTube, laying out the stakes. Could this be the best chance yet to capture high-resolution data on an object from another star? Could it reveal exotic chemistry, or strange outgassing patterns, or a trajectory defying Newtonian expectations? People were primed for answers. They were waiting for the first images, the first press releases, the first sense of wonder, and then, overnight, silence. NASA's website, instead of posting a new image, carried a flat notice about funding lapses. Its social media accounts stopped updating. News reporters calling for comment were told, due to the shutdown, NASA is unable to respond. A crescendo of anticipation collapsed into a void. For the everyday citizen, the effect was chilling. Something extraordinary was happening just out of sight, and the agency charged with showing it to the world had been gagged. This is where logic and emotion diverge sharply. The logical explanation is straightforward. The timing was pure coincidence. The shutdown was triggered by partisan gridlock, not by cosmic events. The telescopes and spacecraft kept operating. The data would eventually be released. No one at NASA was hiding anything. They were simply obeying the law. And yet, the emotional interpretation is much harder to suppress. To see a once-in-history, interstellar visitor coincide with official silence feels orchestrated, whether or not it is. The story writes itself. NASA shuts down just as alien object arrives. Rational minds may reject it, but the human brain is wired for pattern recognition. We cannot help but feel that timing like this carries meaning, and meaning matters. In science, credibility is everything. NASA has built decades of trust by being transparent, by sharing both triumphs and failures in near real time. To break that rhythm at the exact moment of 3I divided by Atlas's arrival risks more than missed headlines. It risks eroding public faith. Silence leaves a vacuum, and in the age of social media, vacuums are quickly filled with speculation. Were strange maneuvers detected? Were unusual emissions observed? Was there something too big to tell us? These questions flourish not because evidence supported them, but because evidence was unavailable. The blackout fed the imagination. For scientists, this dynamic is deeply frustrating. They know the truth is usually mundane, buried in telemetry and error bars. They know that conspiracy theories thrive not on data, but on its absence. And yet, they also know perception matters. Public trust cannot be rebuilt overnight. Each coincidence, each silence, chips away at the foundation. And in September 2024, that foundation was shaken hard. The irony is cruel. At the very moment humanity might have learned the most about interstellar visitors, its most prominent science agency was silent by law. The spacecraft kept watching. The data flowed into secured archives. But to the public eye, nothing happened. An extraordinary event collapsed into an empty feed. It was not the cosmos withholding its secrets. It was us, our own systems, our own politics, our own silence. And so the unnerving coincidence becomes more than just a quirk of timing. It becomes a mirror. It reflects our dependence on fragile institutions, our vulnerability to bureaucratic cycles, and our hunger for meaning when information is withheld. Whether one sees it as a conspiracy or a chance, the emotional impact is undeniable. September 2024 reminded us that sometimes the greatest mysteries are not in the stars themselves, but in the silence between what is observed and what is shared. Around the world, telescopes are still pointed skyward. Amateur astronomers in Spain, Chile, Australia, and Japan tried to track 3I divided by Atlas from Earth's surface. But geometry conspired against them. The object was low on the horizon, near the blinding glare of the Sunday. Observations were difficult, fragmentary, and noisy. Everyone looked to NASA's Mars orbiters as the crown jewels machines, in the right place at the right time, yet the only agency capable of broadcasting those images was offline. It was like standing at the edge of a historic revelation, while the main camera lens was covered with a shutter. That is where the sense of unease deepened. In the vacuum of official silence, social media lit up with speculation. Was 3I divided by Atlas emitting strange bursts? Did its trajectory deviate unexpectedly? Was there something non-natural about its shape, like the elongated puzzle of Oumuamua? Every unanswered question metastasized into a theory. Threads on Reddit, YouTube channels, and podcasts all spinning webs around the absence of data. In truth, the object continued along its path. No evidence yet of anything alien, but perception did not wait for evidence. Perception filled the gap with fear and wonder. The irony is that silence is louder than words. When NASA speaks, its statements anchor the conversation, even if only to say, "We are observing, we will share results soon." But when NASA cannot speak, the anchor is gone. In that drift, narratives multiply, some benign, "It's just bad timing," others dramatic, "What are they hiding?" This is how public trust erodes, not because of lies, but because of silence that feels suspicious. In the 21st century, transparency is not optional. It is oxygen. Take it away, and rumor floods in. For scientists themselves, the frustration was doubled. Imagine being part of a mission team, watching your spacecraft collect data on a once-in-history, interstellar visitor, and being legally forbidden to even acknowledge it. To the scientist, it feels absurd, like being sworn to secrecy not about national security, but about the very purpose of science, discovery. Some vented privately, some wrote drafts to release later, some simply waited. But all of them knew what the public did, not that history was unfolding silently, one data packet at a time. This is where the unnerving coincidence sharpens into a lesson. 3I divided by Atlas reminded us that the universe does not pause for politics. Celestial bodies move to their own rhythm, indifferent to our calendars, indifferent to our shutdowns. If humanity is to truly understand these messengers from the stars, our institutions must be resilient enough to function regardless of political storms. Otherwise, we risk missing not just data, but trust, momentum, and meaning. And yet, even in silence, a paradox emerged. The very lack of information drew more eyes to the story. Mainstream news outlets began asking why NASA was silent, why the timing was so strange, and what 3I divided by Atlas might be hiding. In that void, the object's mystique only grew. By mid-October, 3I divided by Atlas was trending on social platforms not because of what we knew, but because of what we did not. The silence became a magnet. People projected their fears, their hopes, their wildest theories onto it. The shutdown, instead of burying the story, amplified its aura of mystery. But mystery cuts both ways. On one hand, it fuels curiosity. On the other hand, it undermines confidence. If every extraordinary event coincides with bureaucratic silence, how long before the public simply stops believing? How long before science loses its narrative authority? These are not abstract concerns. They shape funding, policy, and the willingness of future generations to trust institutions with the keys to discovery. And so September 2024 stands as a warning. It shows us what happens when cosmic timing collides with human dysfunction. It shows us how fragile our bridge to knowledge really is. A government shutdown might seem like political theatre, but in the realm of science, it is a blackout curtain drawn across the universe. And when that curtain falls, just as a visitor from another star arrives, the world notices. What makes this story so haunting is not just the coincidence itself, but the questions it leaves behind. If a messenger from beyond passes by and the public cannot see it, did we miss more than data? Did we miss our chance to unite in wonder? Did we squander a rare moment of cosmic perspective because of earthly squabbles? These questions hang heavy, unanswered, like the object itself receding into the void. The silence of September 2024 was not just a pause in communication, it was a mirror held up to us. It revealed how much we rely on institutions to carry our collective imagination. It revealed how fragile that reliance is. And it left us with a chilling thought. The universe will keep speaking, but will we always be able to hear? When the screens went black, when NASA's voice fell silent, the immediate instinct was to ask, what are they hiding? But the truth is less cinematic and far more bureaucratic. The silence was not born of conspiracy. It was born of law. Every September, Washington, D.C. becomes a chessboard of budgets, deadlines, and negotiations. The United States operates on a fiscal year that begins on October 1st. If Congress fails to pass a funding bill or a continuing resolution by that date, the government literally runs out of legal authority to spend money. And when that authority lapses, agencies must shut down, not in part, not symbolically, but in a very real and immediate way. NASA, as a federal agency, is no exception. The moment funding expired in September 2024, the Anti-Deficiency Act clicked into place. This law, dating back to the 19th century, prohibits government employees from working without pay unless their duties are deemed essential. Essential means one of two things: protecting human life or safeguarding government property. For NASA, that translates into keeping astronauts safe on the International Space Station, monitoring critical spacecraft so they don't drift into danger, and ensuring mission hardware is not jeopardized. But everything else, the public communication, the press releases, the educational outreach ceases, not because scientists want to stop, but because the law leaves them no choice. This is why, as 3I divided by Atlas edged into Mars's neighborhood, the agency's digital presence froze. The spacecraft kept watching. The raw data still flowed into secure pipelines, but the teams that normally translate that data into tweets, press kits, or live streams were legally barred from doing so. To the outside world, it looked like silence. To the people inside, it was simply compliance. And that is where misunderstanding blossoms. In an age of constant updates, where breaking news arrives by the minute, silence feels unnatural. We equate quiet with secrecy, but shutdown silence is not the same as suppression. It is closer to a pause button. The telescope is still looking, the microphone is just turned off. The difference matters. For conspiracy theorists, it is an opportunity. For rational observers, it is a reminder of how fragile science communication really is, dependent not just on curiosity and instruments, but on the machinery of politics. The irony cuts deep. NASA's mission is to explore and to inspire, yet during a shutdown, the very act of inspiration is categorized as non-essential. The engineers still troubleshoot spacecraft faults. The orbital data still arrives. But the act of telling the story, the part that binds science to society, is silenced. And so, at the very moment the world was hungry to hear about 3I divided by Atlas, the storytellers were forced into legal exile. For the average citizen, this is confusing. Why allow a comet from another star to slip past public attention simply because of a budget dispute? Shouldn't knowledge itself be essential? These are fair questions. They reveal a cultural truth. Science is not just about survival, it is about meaning. Yet the law draws a narrow circle around what counts as essential, and within that circle, meaning does not always fit. So the blackout was not evidence of a cover-up. It was evidence of bureaucracy at work. A frustrating truth, yes, but one that needs to be understood if we are to separate fear from fact. To understand the shutdown's true impact, we need to separate two very different silences: operational silence and communication silence. Operational silence is when the machines themselves stop. A telescope goes offline. A spacecraft fails. A mission loses its heartbeat. Communication silence, on the other hand, is when the machines keep humming, but the humans who normally speak for them are legally barred from sharing. In September 2024, it was the second kind. NASA's orbiters around Mars never blinked. The tracking stations are never powered down. The engineers who protect spacecraft health were still on call, monitoring telemetry, still ready to respond to anomalies. If something endangered astronauts on the International Space Station or threatened the billion-dollar assets orbiting other planets, contingency teams remained active. In that sense, the system did not fail. The exploration continued. What failed, at least in the eyes of the public, was the story. And that distinction is critical. Science is not only about data, it is about context. Without context, raw data is unreadable to most people. Imagine a spreadsheet full of numbers arriving at a secure server in California. To the mission team, it is a treasure. To the public, it is meaningless until translated into an image, a chart, or a headline. That translation is the job of communicators, and during a shutdown, those communicators are gone. The silence the public hears is not the silence of space, it is the silence of absent storytellers. The problem is that perception rarely makes this distinction. For someone refreshing a NASA feed, the absence of updates feels like an absence of discovery. In reality, the data continues to pour in, but because people cannot see it, they imagine that nothing is happening, or worse, that something is being hidden. This is how bureaucratic silence becomes fertile ground for suspicion. The truth is routine, even mundane. But the appearance is dramatic. Here lies the heart of the misunderstanding that fueled speculation about 3I divided by Atlas. The timing created a perfect storm. On one side, a once-in-a-generation interstellar visitor is crossing a window of observation near Mars. On the other hand, the world's leading space agency is muzzled by politics. To the rational mind, the overlap was a coincidence. To the public imagination, it was confirmation of every suspicion. That gap between reality and perception is where conspiracy theories thrive. But clarity matters, and the rational explanation deserves a voice. The reason NASA stopped communicating was not because of what it saw, but because of what it legally could not do. The data was never hidden. It was only delayed. The silence was not a decision by scientists, but a requirement of law. If this distinction seems pedantic, it is because the stakes are so high. Trust in science depends not only on what is true, but on how clearly that truth is understood. So the calm perspective is this. Nothing stopped except the narrative. The spacecraft kept watching, the universe kept unfolding, and when funding resumed, the backlog of data would flow again, ready to be analyzed, interpreted, and shared. It is frustrating, yes. It is inconvenient, absolutely. But it is not the same as a cover-up. The lights were dimmed, not extinguished. And in that difference lies the reassurance. This understanding does not erase the tension of September 2024, but it offers balance. Where others saw secrecy, there was only silence. Where others feared absence, there was only delay. And suppose we remind ourselves of this difference. In that case, the story of 3I divided by Atlas becomes less about suspicion and more about patience, a reminder that sometimes, even in science, the truth takes a little longer to reach the light. The final piece of the puzzle is perspective. To truly understand why the lights went out, we must step back and see the shutdown not as a singular crisis, but as a recurring rhythm of American governance. This was not the first time NASA's communication fell silent. It has happened before, and it will almost certainly happen again. Government shutdowns are a political weapon. Wielded during budget stalemates, they ripple outward, touching every agency, not just NASA. But in NASA's case, the ripple feels seismic because its work is so public, so bound to the imagination of people across the world. In 2013, for example, NASA's websites froze during another shutdown. In 2018, the same happened again. Each time, the spacecraft kept operating. Each time, communication stopped. These moments form a pattern. Exploration continues, but inspiration pauses. To those inside the agency, it is frustrating but familiar. To those outside, it feels like a sudden blackout in a theater just as the play reaches its climax. And when the curtain drops unexpectedly, the audience fills the silence with their own stories. That is exactly what happened in September 2024. As 3I divided by Atlas approached Mars, the silence carried weight far beyond its legal cause. For the casual observer, it looked like a choice. For the skeptic, It looked like suppression. Yet the truth was more ordinary. The law does not distinguish between routine public updates and history-making announcements. It halts them all. That bluntness may seem unreasonable, but it is consistent. NASA was not picking and choosing what to share. It was barred from sharing anything at all. Understanding this consistency is crucial for trust. When we remind ourselves that the silence was applied across the board, not targeted at 3i divided by Atlas, the air clears. The eerie timing remains, but the suspicion softens. It was not that NASA wanted to hide the comet. It was that NASA had to stop talking. Period. The difference may feel subtle, but it changes everything. And so the lesson of why the lights went out is less about cosmic mystery and more about civic reality. Science does not exist in a vacuum. It exists within institutions, and institutions are bound by laws. Sometimes those laws elevate safety above storytelling. Sometimes they delay inspiration in the name of compliance. It is imperfect, yes, but it is not sinister. For the public, the most valuable takeaway is discernment. The next time NASA falls silent during a shutdown, we must ask, is this silence operational or merely communicative? Did the spacecraft stop, or did the storytellers pause? The answer will almost always be the latter, and knowing that distinction allows us to approach the story with calm rather than fear. This is not to diminish the frustration. A once-in-a-generation interstellar visitor passed by, and the silence robbed us of the real-time wonder we craved. That frustration is valid, but frustration is not the same as deception. The truth was never erased, it was only delayed, and in the world of science, delay is an inconvenience, not a conspiracy. As 3i divided by Atlas moved through the skies in late September, the machines kept recording, the numbers piled up, the universe did not stop speaking, only our microphone was temporarily switched off, and when the switch flipped back on, the data would still be there, waiting to be heard. So why did the lights go out? Not because of cosmic secrets, not because of fear of what we might discover, but because the machinery of democracy paused the machinery of storytelling. The stars do not follow our political calendars, and sometimes that clash leaves us in the dark. But the darkness is temporary. The truth, though delayed, always returns to the light. What happens when the universe keeps speaking, but our microphones are turned off? What happens when the very week that could have given humanity its sharpest glimpse of an interstellar visitor is swallowed by silence? That is the unsettling paradox of October 1st to October 7th, 2024, a stretch of time now etched into memory as the dead zone. At first glance, it sounds simple. The government shut down, NASA stopped updating, and 7 days passed. But when you look closer, when you layer the mechanics of spaceflight with the mechanics of bureaucracy, the picture grows darker, because those 7 days were not arbitrary. They were not some routine pause in operations. They were the precise week when 3i divided by Atlas, only the third interstellar object ever seen, passed through a narrow, golden observational window near Mars. In space science, timing is everything. Miss the alignment, and the data is gone forever. Mars, with its orbiters circling faithfully overhead, happened to be in exactly the right position to provide unique measurements of 3i divided by Atlas during that first week of October. For planetary scientists, this was a dream alignment. Orbiters like MAVEN and MRO could have captured spectra of its gases, monitored its dust trail, or at least constrained its brightness profile. Even subtle variations in its light curve might have revealed whether the object was tumbling, fragmenting, or shedding volatile ices. But instead of daily updates, images, or bulletins, what the public saw was nothing. NASA's websites froze on September 30th, stamped with a sterile notice about the funding lapse. Social media accounts went dark. Newsrooms that had prepared to cover the week of the visitor suddenly had no official material to work with. The absence was total. To those outside the secure servers, it was as if history had been erased in real time. This is what makes the dead zone so disturbing. Not that data was never taken, but that it vanished into a sealed box just when anticipation peaked. We know the machines were still recording shutdowns. Do not power down billion-dollar orbiters. Telemetry continued to flow, archived in protected databases. The silence was not in the heavens, the silence was in Washington. And that silence fell over the exact 7 days. Curiosity burned hottest. To the rational mind, the explanation is bureaucratic. The Anti-Deficiency Act forbids non-essential work during a shutdown, including communication. Simple cause and effect, but emotionally, it feels intolerable. This was not some routine weather update or postponed press release. This was humanity's third brush with an object from beyond the Sunday. And in the 1 week we needed clarity most, the lights went out. This is where forensic thinking is essential. We cannot allow suspicion to replace analysis, nor can we shrug the timing off as meaningless. The correct approach is to ask precise questions. Asterisk. What data should have been produced during October? 1. 7. Spectra. Light curves. Positional measurements. Asterisk. What constitutes a normal delay? In previous shutdowns, data has resurfaced weeks later, often bundled as backdated releases. Asterisk. When does a delay become suspicious? If months pass after the shutdown ends and the Mars data remains unpublished, that signals something more than bureaucracy. This checklist is the key to separating ordinary gaps from extraordinary ones. Without it, rumor thrives. With it, we hold institutions accountable while keeping our logic intact. The first forensic principle is that spacecraft keep running. Maven does not care about congressional calendars. Its instruments operate on schedules written months in advance. That means raw files almost certainly exist for October 17. The second principle is that NASA's blackout is absolute. It does not discriminate between trivial updates and historic ones. When the law says stop, it stops everything. The third principle is the most painful. Cosmic events do not wait for politics. If the government is dark, the comet still shines, and that overlap creates irretrievable loss not of the science itself, but of the shared, public moment. Because science is not just numbers. It is a story. It is the act of witnessing together. And when that act is denied, trust begins to erode. People feel excluded from their own future. They fill the void with their own narratives. Some imagine that nothing happened. Others imagine that everything happened and was covered up. Both are distortions, born from absence. That is why the dead zone matters. It is not merely a footnote in the log of a shutdown. It is a reminder of how fragile our connection to the cosmos really is. It shows us that even in an era of orbiters, supercomputers, and global networks, our ability to experience discovery together can vanish in the span of a week. And it leaves us bout root, unsettled, caught between logic and longing. If the first step in understanding the dead zone is recognizing that the data almost certainly exists, the second step is asking, what exactly might have been lost or at least delayed in those 7 days? Here is where the bout root grows sharper, because the potential stakes are not abstract. They are measurable, and they matter. For planetary scientists, the week of October 17, 2024 represented a narrow corridor in geometry. 3. I divided by Atlas, racing on its hyperbolic path, aligned in such a way that Mars orbiters could have provided a side-angle view of its coma and trajectory. That geometry would never repeat. Even a delay of a few days altered the line of sight, the angle of reflection, and the background glare from the Sunday data missed during that window is simply unrecoverable. No second chances, no do-overs. So, what might have been in those packets of silence? Asterisk brightness variability. A 7-day run of light curves could have revealed whether the object was tumbling chaotically or rotating steadily. Rotation rates tell us about shape, density, and internal cohesion. Miss a week, and the pattern can never be fully reconstructed. Asterisk spectral fingerprints. Instruments like Maven's IUVS could have measured gases in the coma. Did it contain exotic molecules unseen in local comets? Did it match Oumuamua's strange lack of a typical tail? Those answers hinge on time-specific exposures. Asterisk, outgassing behavior. Jets of gas or dust, if present, could nudge the object's orbit slightly. Detecting such perturbations requires continuous monitoring. A 7-day hole in the record makes it harder to distinguish natural variability from true anomalies. Individually, any one of these measurements may seem small. Collectively, they tell the story of what 3I divided by Atlas really is. And the dead zone means that the story is incomplete, at least for now. The forensic way to process this unease is to build a checklist of explanations. 1. Routine gaps. It is normal for spacecraft data to be archived internally before public release. Sometimes weeks pass, even in non-shutdown periods. 2. Shutdown backlog. Once funding resumes, staff need time to process, verify, and upload. That delay could account for silence even after the weekends. 3. Anomalous delay. If months go by without those October 17 datasets appearing, then questions grow serious. Was the data corrupted? Was it deprioritized? Or is something being withheld? Until the backlog clears, no conclusion is safe. But the presence of a gap, precisely aligned with a critical celestial window, ensures that suspicion will linger. That is why the dead zone is more than silence, it is an open question mark. And this is where the public perception diverges most from scientific patience. Scientists understand delays. They live with them. Daily peer review takes months, mission reports years. But the public lives on the clock of headlines, of instant access, of real-time feeds. For them, 7 days of nothingness at the peak of curiosity feels like a betrayal. The rational voice says, "Be patient, the data is safe." The emotional voice says, "Why does it feel like someone pulled the curtain just as the show began?" The tension is not just academic, it is cultural. In an age where mistrust of institutions runs high, the dead zone feeds existing skepticism. People do not measure silence by laws, they measure it by emotion. They remember the drama of Oumuamua's unexplained acceleration, the debates about whether it was a comet, asteroid, or artifact. They recall 2I divided by Borisov's exotic chemistry, and they wonder, could 3I divided by Atlas have been even stranger, its secrets locked away by a timing quirk too perfect to ignore? This is why the but-root will not fade quickly. The forensic facts can say, the silence was procedural, but the psychological effect is deeper. When silence overlaps with significance, humans sense a pattern. We are wired that way, and the dead zone, 7 days long and perfectly timed, is almost too neat a pattern to dismiss emotionally. So we are left with 2 truths coexisting uneasily. 1. The data is real, it will likely surface, and the silence was mandated by law. 2. The public moment was lost forever, leaving a scar of distrust. Together, they make the dead zone not just a technical footnote, but a symbolic rupture. It is both an explanation and an open wound. If there is a single word that defines the dead zone, it is limbo. For 7 days, the public lived in a space between certainty and speculation, between science and silence, and the unsettling part is that limbo leaves lasting marks. Even once the shutdown ended and NASA's staff returned to work, the memory of those missing days did not vanish. Instead, it became a prism through which all future data would be judged. When, weeks later, NASA released its first post-shutdown updates, many readers did not simply take the information at face value. They looked for signs of editing. They asked, is this really what was recorded, or is it what they want us to see? That suspicion was not born from evidence, but from absence. In the forensic sense, the dead zone had already contaminated the chain of custody. Data released late is always more vulnerable to doubt, because the public cannot verify whether it was altered in the interim. The timing alone is enough to strain trust. This is why analysts insist that gaps must be contextualized. Not all data gaps are sinister. Spacecraft suffer glitches, telemetry gets delayed. Sometimes the geometry simply does not allow for clean measurements. But when the gap coincides with a once-in-a-lifetime event, the weight is magnified. The October 17 silence carries more psychological gravity than a random downtime in March ever could. Context transforms delay into drama. So, how do we process this without succumbing to paranoia? The checklist approach offers a path. First, confirm that the instruments were operational. If Maven's logs show nominal function during the shutdown, then the data exists. Second, check the release pipeline. If the October datasets appear in full once staff are back online, the gap is procedural, not intentional. Third, watch for inconsistencies. If frames are missing, timestamps misaligned, or metadata redacted, those anomalies warrant scrutiny. This approach does not erase unease, but it channels it into structured analysis. Suspicion becomes a hypothesis, and a hypothesis can be tested. Still, even the best checklist cannot erase the human response. The boot root of the dead zone is not only about science, it is about belonging. People want to witness discovery together. They want to feel the moment unfold in real time. Deny them that, and they feel excluded. And exclusion breeds mistrust. This is the cultural cost of shutdown silence, a cost far higher than missed tweets or delayed press releases. It is the cost of eroding the bond between science and society. The irony is that the scientists themselves share this frustration. For them, the dead zone was not a cover-up, it was a cage. Teams that had worked for years to prepare for interstellar visitors found themselves powerless to share their triumphs. Imagine sitting at a console, watching your spacecraft beam back data on a comet from another star, and being legally forbidden to tell anyone. That frustration mirrors the public's, but with even sharper edges. It is not just the audience left in limbo, it is the performers themselves. And so the dead zone leaves us with a paradoxical legacy. On one hand, it is a case study in bureaucracy, the inevitable byproduct of laws designed for accountability. On the other hand, it is a symbol of how fragile our connection to discovery can be. For 7 days, humanity had front-row seats to the universe, and yet the curtain stayed closed. No matter how many images are eventually released, no matter how many papers are published later, that shared moment is gone. Perhaps this is the greatest lesson of October 2024, that silence, even when procedural, is never neutral. It reshapes perception. It alters memory. It writes its own narrative. For some, the dead zone will always be proof of concealment. For others, it will remain an example of bureaucratic bad luck. But for all, it will be a reminder that cosmic timing and human timing rarely align, and when they clash, history sometimes slips through our fingers. The story of 3I divided by Atlas did not end in those 7 days. The comet continued on its path, the orbiters kept recording, and the data would eventually reach the light. But the emotional imprint of the dead zone lingers. It is a scar across the timeline of discovery, a chapter defined not by what was seen, but by what was not shared. And in that absence lies both a caution and a challenge. To build systems resilient enough that when the next messenger from the stars arrives, we will not find ourselves trapped in silence again. Numbers don't lie, but they can unsettle us when they describe a path that does not belong here. Every calculation of 3I divided by Atlas's orbit shouts the same truth. This object is not bound to the Sunday. It came from beyond, and when it leaves, it will never return. To understand why astronomers are certain of its interstellar origin, we have to talk about orbital math. Most comets and asteroids follow ellipses. An ellipse means they are tied to the sun, swinging around it endlessly like beads on a cosmic string. But 3I divided by Atlas traces something different, a hyperbola. A hyperbolic orbit is open-ended, its curve shaped not by loyalty but by escape. Objects on hyperbolic paths arrive fast, dive near the sun, and then slingshot back into interstellar space, never to repeat. Mathematically, it is the difference between an eccentricity less than 1 and an eccentricity greater than 1. 3I divided by Atlas's eccentricity, calculated in late 2024, was above 1. That single number, more than any headline, is the fingerprint of a traveler from the stars. But orbital math is not just about labeling an object, interstellar or not. It is about prediction. Every observation of 3I divided by Atlas's position, each point of light traced against the starfield is fed into models that calculate its trajectory. These models use Newton's laws, refined with relativistic corrections, to predict where the object will be tomorrow, next week, and next month. When the models and the observations agree, confidence grows. When they diverge, suspicion stirs. Here is where the concept of perturbation enters. A perturbation is simply a deviation from the predicted path. In planetary dynamics, perturbations are everywhere. The gravitational tug of Jupiter, the gentle drag of solar radiation, the push of gases venting from a comet's surface, these all create nudges that shift trajectories slightly. Normally, perturbations are small, expected, and explainable. But with interstellar objects we watch more closely. Oumuamua, for example, showed a puzzling acceleration not fully explained by outgassing. That anomaly fueled years of debate, from mundane dust jets to exotic hypotheses. With 3I divided by Atlas, scientists are determined to measure every nudge with forensic precision. The challenge is that the closer 3I divided by Atlas came to perihelion in late October 2024, the harder it became to measure. Its angular distance from the Sun grew small, drowning it in glare. Ground-based telescopes struggled. That left orbiters and space-based instruments as the best tools for monitoring perturbations. Their data feeds into a delicate balance. the equations predicting a path and the reality of how that path bends under subtle forces. And this is where the calm perspective is vital. A deviation does not automatically mean something extraordinary. It means something physical is happening. Perhaps jets of gas are erupting as the object heats near the sunday. Perhaps faint interactions with the solar wind are stronger than modeled. The forensic approach is to map the discrepancy, compare it with known physics, and see whether the numbers line up. Only if they don't, only if the deviations exceed what physics can explain, does the question of anomaly arise. So when the public hears talk of perturbations, the calm reminder is this: perturbations are normal. They are the fingerprints of physics at work. What matters is how big they are, how consistent they appear, and whether they can be traced back to known causes. In the case of 3I divided by Atlas, the story was still unfolding in late October 2024. The math said hyperbolic, interstellar. The signals hinted at subtle forces nudging its path. The task was not to panic, but to measure, and in the measurement, to understand. If orbital eccentricity proves that 3I divided by Atlas is interstellar, then perturbations tell us how it behaves under stress. Think of the object as a test particle drifting through a storm. Gravity pulls it one way, sunlight pushes another, and internal ices may jet outward in invisible spurts, adding their own unpredictable thrusts. The dance of these forces writes itself into the orbital record, visible as tiny deviations from prediction. The key forensic question is always, are the deviations within expected bounds? To answer, scientists break perturbations into categories. The first is gravitational perturbations. These are predictable, caused by the tugs of planets, primarily Jupiter. Astronomers can model these with exquisite precision. If the path curves in line with Jupiter's pull, the math is satisfied. The second is non-gravitational perturbations, often trickier. Comets, when warmed by sunlight, vent gases. Those outgassing jets act like miniature thrusters, altering velocity by fractions of a meter per second. Over weeks, those fractions accumulate into measurable shifts. If the timing of the deviation matches the heating curve of the comet, the explanation holds. Where it grows interesting and unsettling is when deviations appear, but neither gravitational nor standard outgassing fully account for them. Oumuamua sparked exactly this debate. Its acceleration was small but significant, and it did not display the obvious coma or tail typical of gas-driven motion. Was it an unusual fragment of hydrogen ice sublimating invisibly? Was it shaped like a thin pancake, pushed more strongly by radiation pressure? Or was it, as some speculated, something entirely different? These debates highlight why perturbations matter. They are the fine print in the cosmic record. With 3I divided by Atlas, the late October 2024 perihelion offered the best chance to spot such fine print. As the object dipped to 1.36 AU from the Sun, heating peaked. If ice were buried in its surface, it should have erupted then, pushing the orbit slightly off the pure hyperbola predicted by Newton's laws. Detecting that push required continuous measurements of its position against background stars precise down to arcseconds. Any consistent drift could indicate non-gravitational acceleration. And here is where patience and calm reasoning must balance the unease. A perturbation is not automatically extraordinary. It becomes meaningful only when the magnitude exceeds physical expectation or when it resists every plausible natural explanation. That is why astronomers treat these analyses with caution. They run the numbers repeatedly, accounting for every variable, from solar flux to instrument bias. If the deviation survives all that scrutiny, then, and only then, does it rise to the level of anomaly. For the public, this process can feel agonizingly slow. News headlines crave certainty. They ask, is it natural or not? But orbital math does not yield answers that quickly. It demands rigor. It demands comparison against decades of cometary behavior. It demands the calm accumulation of evidence, one calculation at a time. And yet, in that slowness lies the safeguard. Without it, every wiggle in a data plot would be mistaken for the extraordinary. With it, anomalies are rare but real. This is where the true educational value lies. By watching how astronomers handle 3I divided by Atlas, we see science in its most honest form: methodical, skeptical, cautious. Numbers are tested, retested, and only reluctantly interpreted. That approach is not designed to excite, it is designed to protect against error, and in the realm of interstellar visitors, error is unacceptable. With only 3 such objects ever observed, each data point is precious. Losing one to haste would be as tragic as losing it to silence. So, as the perihelion of October 2024 came and went, the tension was not in whether 3I divided by Atlas was alien. It was whether its small orbital deviations matched the physics we already know. And the calm truth is this: perturbations always exist. The question is whether they fall within the boundaries of reason or whether they spill beyond into the realm of mystery. In the weeks after perihelion, astronomers began consolidating the data. Position measurements from different observatories were combined into refined orbital solutions. This is the stage where the forensic process truly shows its power. Each observation is like a breadcrumb. Alone, it tells little, but strung together, the trail reveals whether 3I divided by Atlas is following the predicted hyperbola or slipping away from it in subtle, telling ways. One of the calm reassurances here is that orbital math is mercilessly transparent. The equations that describe motion under gravity are not mysterious. They are centuries old, tested against planets, comets, and spacecraft. If 3I divided by Atlas diverges from prediction, the divergence will be measurable, and the measurement will have to fit into some physical box. There is no room for magic in Kepler's laws. What there is room for, however, is discovery. Discovery of what physical processes are strong enough to push an object from beyond the stars off its expected path. By early November 2024, preliminary fits showed that 3I divided by Atlas was still securely on a hyperbolic escape trajectory. The eccentricity remained greater than 1, meaning it was indeed interstellar. That part was never in doubt. What remained under study were the perturbations, the small deviations from perfect prediction. Did they line up with models of outgassing? Did they match the solar radiation pressure expected for an icy body of its estimated size? Or did something else linger in the numbers, something harder to explain? Here, the mood among scientists was a blend of patience and quiet excitement. Patience, because teasing out perturbations requires weeks, even months, of statistical analysis. Excitement, because anomalies, if confirmed, can reshape understanding. But even in that excitement, the tone remained cautious. No one wanted a repeat of the Oumuamua debates, where interpretations leapt ahead of evidence. The lesson from that controversy was clear. Wait for the math to settle before making claims. For the public, this waiting game can feel anticlimactic. The drama of an interstellar visitor seems to demand instant revelation. But the true drama lies in the numbers themselves, the careful sifting, the search for patterns, the testing of every possible explanation. That slow, deliberate process is not an obstacle to wonder. It is the very engine of it. Because when, after months of work, a deviation is finally confirmed as real and unexplained, that wonder is grounded. It is not speculation. It is evidence. And this is where the calm perspective matters most. If the perturbations of 3I divided by Atlas turn out to be entirely explainable by outgassing and sunlight, that is not a disappointment. It is a triumph of physics, another confirmation that the laws we trust still hold, even for messengers from other stars. If, however, something remains unaccounted for, then the scientific process will not leap to conclusions. It will expand its search, test new hypotheses, and invite the scrutiny of peers worldwide. Either outcome is valuable. Either outcome is discovery. The orbit math of 3I divided by Atlas, then, is not a story of panic but of patience. It is not about expecting the extraordinary at every turn, but about letting the numbers speak clearly. In a world saturated with speculation, the measured voice of orbital dynamics is a balm, steady, precise, unhurried. It reminds us that science does not rush to satisfy curiosity. It moves carefully to protect the truth. So, as 3I divided by Atlas fades back into the darkness, leaving the solar system forever, its path is not only written in the stars but inscribed in equations. Equations that balance logic with curiosity, reason with wonder. And in those equations, we find the calm reassurance that the universe, no matter how strange its visitors, still dances to laws we can know, measure, and trust. What if the most powerful camera orbiting Mars, the very same lens that can spot a rover wheel, or even a parachute on the surface, was still practically blind to a visitor from another star? That is the sobering reality of trying to image 3I divided by Atlas with HiRISE in early October 2024. HiRISE, The high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter is legendary for its clarity. From 300 kilometers above the Martian surface, it can capture features smaller than a coffee table. We've seen breathtaking images, dust devils spiraling across dunes, tracks left by Curiosity, even the tiny shimmer of InSight's solar panels. To the public, HiRISE feels almost omnipotent, a cosmic zoom lens that can reveal anything. But the reality is harsher. Its power comes from proximity. It is designed to image Mars, not deep space, and when pointed outward toward an object millions of kilometers away, its resolution collapses. Here is the math that grounds expectation. At Mars orbit altitude, HiRISE achieves about 30 centimeters per pixel on the surface, but 3i divided by Atlas, during its closest approach relative to Mars in early October 2024, was nearly 30 million kilometers away. At that distance, the same detector cannot resolve features meters across. It can only register blobs tens of kilometers wide. In fact, the effective scale is about 30 kilometers per pixel. To put that into perspective, if 3i divided by Atlas were the size of a mountain, HiRISE might register it as a single dot of light. If it were closer to the scale of a city block, it would disappear entirely into a single unresolved pixel. This is the first reality check. Even our sharpest Martian camera becomes almost blind when stretched to interplanetary distances. It was never designed to act like Hubble or JWST, whose optics and orbits are tailored for deep space imaging. HiRISE is brilliant at what it does, mapping Mars in exquisite detail, but it cannot transform into a cosmic telescope simply because we wish it so. And this is why expectation management is critical. When the public hears NASA's powerful camera will look at the interstellar comet, imaginations leap to cinematic visions, crisp photos of a glowing visitor, maybe even surface detail. The reality is far more modest. At best, HiRISE could contribute photometric data, measuring how the object brightens or dims, helping to refine its rotation or surface properties. That kind of science is valuable, but it looks nothing like the stunning images people expect. The geometry of observation adds further complications. 3. I divided by Atlas approached near the line of sight to the Sun, a condition astronomers call low solar elongation. This glare makes observations from Earth-based telescopes extremely difficult, sometimes impossible. Orbiters at Mars offered a better angle, but even they were working against the brightness of scattered sunlight. In other words, the challenge was not just distance, but also lighting. Trying to see 3i divided by Atlas was like trying to photograph a firefly flying near a stadium spotlight. These limitations matter because they explain why the October 2024 window, despite being so anticipated, did not yield the cinematic breakthroughs many hoped for. The instruments did their job. They gathered data, but the kind of data possible under those conditions is subtle, incremental, not spectacular. And unless the public understands this, silence feels suspicious. In truth, it is simply the boundary of physics and engineering. So the first part of the lesson is clear. Even the sharpest eye at Mars has limits. The gap between expectation and reality is wide, and unless that gap is acknowledged, disappointment grows. HiRISE did not fail. It performed as designed. The problem lies not with the camera, but with our hopes of what it could show us. If resolution was the first barrier, brightness was the second. Even if HiRISE could register a dot of light from 3i divided by Atlas, the question remained, how bright would that dot be against the cosmic backdrop? Here, the geometry worked against us. By early October 2024, the comet was approaching perihelion, the point of closest distance to the Sun. That meant it was sitting in the worst possible part of the sky for observation, low elongation, where the sun's glare drowns out faint objects. Astronomers compare it to trying to spot a candle flame inches away from a car's high-beam headlights. From Earth, ground-based telescopes struggled. Even large observatories with adaptive optics had difficulty pulling a clean signal out of the wash of sunlight. From Mars orbit, the angle was slightly better, but still challenging. HiRISE was not designed to capture faint objects set against brilliant glare. This is where expectation and reality diverge most. When the public hears interstellar visitor, they picture dazzling tails, fiery streaks, and Hollywood-level spectacle. But in truth, 3i divided by Atlas never became a naked-eye comet. Its coma was faint, its tail was diffuse. Even sensitive detectors measured it as a modest smudge. To instruments like HiRISE, the task was less like photographing a glowing beacon and more like measuring the flicker of a weak bulb in daylight. That is valuable science, but it does not translate into breathtaking imagery. Still, the faintness of the object should not be confused with insignificance. Even a single pixel of light carries information. Scientists use brightness curves to infer rotation rates, shapes, and surface properties. By measuring how the dot brightens or dims over time, they can deduce whether the object is spinning, whether its surface reflects light evenly, or whether jets of gas are creating asymmetry. In this sense, HiRISE's potential contribution was not visual beauty, but quantitative precision. Numbers, not pictures, curves, not postcards. This is where the forensic explanation helps reduce suspicion. Many people ask, if NASA really turned HiRISE on 3i divided by Atlas, why don't we see the pictures? The honest answer is, because the pictures look underwhelming. A single speck against a black sky does not inspire clicks. But for astronomers, that speck, when measured carefully, holds secrets. The science is subtle. The story it tells takes time, and when expectations are set too high, subtlety feels like an absence. Lighting also introduces noise. Detectors are not perfect. They capture background cosmic rays, scattered sunlight, and thermal interference. Sorting the signal of 3i divided by Atlas out of that noise requires post-processing, calibration, and cross-checking against other instruments. During a shutdown, none of that public-facing processing happens. So what appears to the public as silence is, in reality, the slow forensic work of turning faint specks into trustworthy science. And this is where the calm, realistic perspective becomes essential. The value of HiRISE was never to deliver a glossy portrait. It was to add another layer of measurement to the global campaign to study 3i divided by Atlas. Think of it like a detective case. One witness describes a figure in the dark, another records footsteps, a third hears a faint sound. No one witness gives you the full story, but combine them, and the truth sharpens. HiRISE's faint dot was one such witness. Not glamorous, not definitive, but crucial in context. So when disappointment set in, when no dramatic images emerged from Mars, the forensic answer was not that NASA hid them, but that the images themselves were modest to the point of being anticlimactic. The science was real, the data useful, but the spectacle never existed to begin with. To recognize that is not to diminish the mission, but to align expectations with reality. And in that alignment, trust is rebuilt. The third and perhaps most important barrier is psychological. The expectation gap. Instruments like HiRISE live in the imagination as miracle machines. For years, the public has been treated to jaw-dropping images from Mars river valleys in razor-sharp detail, tracks left by rovers like breadcrumbs across the desert floor, even parachutes frozen mid-descent. Each of these images reinforces the sense that NASA can show us anything, anywhere, anytime. But when it comes to interstellar visitors, that expectation collides with physics. 3i divided by Atlas forced a reckoning. The very idea of pointing HiRISE at an alien comet suggested a cinematic payoff. Journalists wrote headlines. Social media speculated about crisp portraits of a visitor from beyond the stars. And when those portraits never materialized, when all that existed was a faint, noisy dot, disappointment turned to suspicion. Silence became interpreted not as a byproduct of physical limits, but as deliberate withholding. This is the expectation gap at its sharpest. The difference between what people imagine science can deliver and what science is actually equipped to provide. Bridging that gap requires honesty. Scientists must explain, patiently but firmly, what data can and cannot show. They must say clearly, HiRISE cannot resolve a comet 30 million kilometers away into anything more than a point source. That statement may deflate excitement, but it prevents confusion later. It reframes the mission. The value lies not in a photograph to hang on a wall, but in the numbers hidden within that pixel. Spectral calibration, brightness, variability, comparative geometry. These are not headline grabbers, but they are the foundation of discovery. The forensic perspective here is liberating. It tells us that disappointment is not the same as deception. The absence of Hollywood images is not evidence of a cover-up, but proof of honesty about limits. And those limits are not failures, they are reminders of the scale of the universe, of how small even our best instruments are against the vastness of interstellar space. Think of it this way. If HiRISE had captured a faint dot, and if that dot showed slight flickers over hours, scientists could model its spin, estimate its shape, even constrain its density. That is extraordinary science from a single pixel, but to the public eye, it looks like nothing more than a grain of dust on a photograph. Without translation, the meaning is lost, and when meaning is lost, imagination fills the void with disappointment at best, suspicion at worst. This is why the October 2024 Mars window was never about breathtaking photos. It was about calibration. It was about cross-checking ground-based observations, blinded by solar glare, with an orbiting camera in a different geometry. It was about pulling one more thread of evidence into the tapestry of what 3i divided by Atlas truly is. By itself, HiRISE could never have solved the mystery. But combined with spectral data from Earth telescopes, with dynamical models of its hyperbolic orbit, with brightness curves tracked by amateurs worldwide, it became part of a global chorus of measurement. The calm reality is this: science is rarely cinematic in real time. It is patient, cumulative, and precise. Expecting HiRISE to hand us a dramatic portrait of 3i divided by Atlas was always unrealistic. The real contribution was subtler, refining orbital models, confirming brightness trends, ruling out extreme anomalies. These outcomes may not go viral, but they are the quiet victories that build truth. So the lesson of HiRISE and 3i divided by Atlas is not disappointment, but perspective. Instruments have limits. Geometry imposes constraints. Data may appear underwhelming, yet still hold immense value. If we let go of Hollywood expectations, we can appreciate the quiet elegance of a single pixel carrying the weight of interstellar history. And in that appreciation, we find trust, not in spectacle, but in reality. What happens when the laws of politics override the laws of curiosity? When congressional gridlock, funding rules, and classification protocols dictate not just how data is handled, but when and whether it ever reaches the public? That is the uncomfortable intersection where NASA's mission to explore meets Washington's machinery of policy. By late 2024, after the September shutdown, the silence surrounding 3i divided by Atlas became a case study in this tension. On the surface, the explanation was simple. The Anti-Deficiency Act forced NASA into compliance, halting public communication until funding returned. But beneath that procedural layer lies a web of agency, politics, and classified protocols that complicate how and how quickly information flows. For those outside the system, the silence feels like a cover. For those inside, it feels like routine. The truth, as always, is somewhere between. The first layer of this truth is continuity of operations planning. COOP. Every federal agency has one. It defines what continues during a shutdown and what stops. For NASA, essential includes keeping spacecraft alive, monitoring astronaut safety, and protecting billion-dollar assets. Non-essential includes press releases, outreach, and even some scientific coordination. But COOP does more than split tasks. It creates a hierarchy of access. Certain mission staff remain on duty, certain data pipelines stay open, but others are locked. Even within NASA, information becomes compartmentalized. The public sees silence, but even some scientists outside mission-critical teams experience delay. The second layer is interagency politics. NASA is not an island. Its missions overlap with the Department of Defense, with NOAA, and with international partners like ESA. Each brings its own rules, priorities, and sensitivities. When a shutdown or a sensitive event coincides with a mission, clearance can become tangled. Data might be held, not because it is shocking, but because it touches another agency's jurisdiction. A Mars orbiter's observations, for instance, might pass through channels also used by defense satellites. That overlap triggers caution. The silence in October 2024 was procedural, yes, but it was also shaped by interagency caution. The third layer is classification protocols. Here is where public perception diverges most from bureaucratic reality. When people hear classified, they imagine alien secrets, shocking discoveries hidden from humanity. The truth is more mundane. Classification often protects technology, not discovery. Resolution capabilities, sensor calibration, transmission channels, these are details adversaries might exploit. So sometimes, even benign space data gets delayed or redacted because revealing it too quickly exposes sensitive technical information. The science itself may be ordinary, but the process of collection is not. That distinction rarely makes headlines, but it matters deeply. Forensic analysis of these three layers shows why the October 2024 silence felt sharper than usual. It was not just a government shutdown, it was a convergence. A shutdown, freezing public communication, interagency caution, slowing coordination, and classification protocols filtering release. Put together, they produced the impression of a blackout, but each component, by itself, was procedural. This is why caution must frame our understanding. The absence of updates during those days was not evidence of a conspiracy. It was evidence of a system designed, sometimes over-designed, to minimize risk. Risk of wasting taxpayer money, risk of compromising safety, risk of exposing technology. None of these motives thrills the imagination, but they explain the silence more convincingly than speculation ever could. And yet, the optics remain brutal. To the public, the silence fell just as 3I divided by Atlas crossed its Martian window. To skeptics, that was too perfect to ignore. To insiders, it was just bad timing. Bridging that divide requires more than equations or reassurances. It requires honesty about the messy reality of agency politics and humility about how much of discovery is shaped not by stars, but by statutes. If continuity planning and interagency overlap explain part of the silence, the politics of perception explain the rest. Washington is acutely aware that space missions are not just scientific, they are symbolic. Every announcement carries weight. Every delay breeds suspicion. And when the stakes involve an interstellar visitor, like 3I divided by Atlas, the politics of timing become as important as the data itself. Consider how narratives are shaped. If NASA announces preliminary results too quickly, it risks being wrong, which damages credibility. If it waits too long, it looks evasive. That narrow corridor of communication, say too little, and the public feels betrayed. Say too much, and rivals exploit details, creates pressure from all sides. In late 2024, during the shutdown aftermath, NASA was trapped, legally barred from communicating during the funding lapse, then politically pressured to manage expectations after. It could never fully satisfy either side. This is where caution enters. Agencies know that raw data, without context, can spiral into conspiracy. A fuzzy dot released without explanation will be dissected online as evidence of a cover-up. A delayed release of the same dot will be spun as proof of editing. Both interpretations are wrong, but perception often trumps reality. That is why NASA and its partners lean toward deliberate pacing. Better to release carefully explained data than to flood the public with raw, easily misinterpreted fragments. The thun-trong tone, then, is not a signal of suppression but of damage control. Agency leaders have lived through this before. Oumuamua in 2017, where ambiguous acceleration data ignited debates that still smolder today. They remember how communication gaps created fertile ground for speculation about alien probes. No one inside NASA wants a repeat. And so with 3I divided by Atlas, the instinct was caution. The data would be shared but framed carefully, with context strong enough to survive public scrutiny. This instinct for caution also intersects with classified projects. Here, the stakes become more obvious. Some instruments orbiting Mars are dual-use, serving both scientific and defense purposes. Their raw performance data reveals capabilities that adversaries would love to map. Revealing too much, too soon, risks compromising national security. The safest course is to delay, redact, or route data through controlled pipelines. To the public, that looks like silence. To insiders, it looks like prudence. Again, the optics differ dramatically from the reality. The irony is that this very prudence feeds mistrust. By protecting credibility and security, NASA inadvertently fuels suspicion. People conflate caution with cover-up, failing to see the bureaucratic logic behind the pause. This tension is not unique to 3I divided by Atlas. It runs through every classified adjacent project. But because 3I divided by Atlas was interstellar, the tension became amplified. A cosmic rarity collided with earthly caution, and the result was an information vacuum filled with doubt. Forensic reasoning helps untangle this. 1. Recognize the legal baseline shutdown law forbids public communication, no exceptions. 2. Recognize the political filter announcements are timed to protect credibility. 3. Recognize the classified overlay data handling is shaped by security concerns. When these three align, silence is almost guaranteed. It is not evidence of conspiracy. It is evidence of overlapping caution. Yet this understanding does not erase the frustration. Scientists want to share, the public wants to know. Both groups are caught in the middle. That is why the October 2024 case study matters. It shows us how fragile the chain of communication really is, and how easily politics can bend the flow of discovery. It warns us that the silence around 3I divided by Atlas was not an accident, but the predictable result of a system designed to err on the side of caution. And so the lesson is sobering. Curiosity may drive exploration, but politics governs communication. Between those two forces lies the space where trust is either built or lost. The final layer of this story is the one least visible but most persistent, the culture of secrecy that hovers at the edge of every space program. Not secrecy in the cinematic sense of hidden spacecraft or alien encounters, but secrecy as a bureaucratic habit. Agencies that handle sensitive technology default to caution. Silence becomes the safest answer. And over time, that habit shapes how missions like 3I divided by Atlas are perceived. Within NASA, most scientists are committed to transparency. Their careers depend on publishing data, collaborating internationally, and building open archives. Yet they work alongside engineers, administrators, and policymakers who must think in terms of security and liability. A spectrometer's calibration file might look trivial to a researcher, but to a defense analyst, it reveals the sensitivity of a detector. A delay in releasing raw frames may frustrate a grad student, but for an administrator, it reduces the risk of a public relations firestorm. Each choice is rational within its silo. Together, they create a culture where silence often feels safer than speed. In late 2024, as 3I divided by Atlas swept past Mars, that culture showed its full weight. The shutdown had already frozen communication. Interagency overlap had introduced more caution. Classification protocols filtered the rest. By the time normal operations resumed, the instinct for restraint was entrenched. Better to explain slowly, better to release selectively, better to frame carefully. From the outside, it looked like deliberate concealment. From the inside, it looked like responsible stewardship. The two perspectives could not be more different, yet they described the same actions. This is where Thuntrong becomes the essential lens for the public. When faced with gaps, the easy path is suspicion. The harder but more accurate path is to ask, does this gap fit the pattern of bureaucracy? In the case of 3I divided by Atlas, the answer is yes. The silence fits perfectly with the rules of shutdown, the culture of interagency caution, and the protocols of classification. It is unsettling, but it is not extraordinary. The very ordinariness of the explanation is what makes it so unsatisfying. Still, the consequences cannot be dismissed. Each time silence overlaps with significance, public trust erodes a little further. Each time the optics suggest a cover-up, more people stop believing the rational explanation. And trust, once lost, is far harder to regain than data delayed. That is why the politics of agency communication matter so much. They are not just procedural, they are existential for public credibility. The lesson of October 2024, then, is not about what 3I divided by Atlas revealed, but about what the silence revealed. It showed us the fragility of the bridge between science and society. It showed us that even in the absence of conspiracy, caution can look conspiratorial. And it showed us that if agencies want to protect both credibility and security, they must find new ways to communicate honestly about their limits. A single sentence, data is being collected but cannot be shared until operations resume, might have prevented weeks of suspicion. Silence without explanation is the oxygen of doubt. So, as we look back on the politics that framed the arrival of 3I divided by Atlas, the conclusion is both logical and sobering. The silence was real. It was procedural. It was shaped by agency politics and classified caution. And while it did not hide cosmic secrets, it did expose a more terrestrial one, that our institutions are not just explorers of the stars, but prisoners of their own rules. In that truth lies the challenge for the future. To explore boldly, we must also communicate bravely. To maintain trust, agencies must not only gather data but also share the constraints honestly. Otherwise, every silence will echo louder than the science itself. If we place every event on a single line, the mystery of 3I divided by Atlas shifts shape. What looks like deliberate silence in isolation often looks like nothing more than scheduling when seen as a sequence. The power of a timeline is clarity, and clarity, if we have the patience to trace it step by step, is the antidote to suspicion. The story began on July 1st, 2024, when astronomers poring over wide-field survey images noticed a faint streak. At first, it looked like another long-period comet, one of dozens logged every year. But orbital calculations quickly overturned that assumption. Its eccentricity was above 1, meaning its path was hyperbolic. A hyperbolic orbit means escape, not return. This was not a comet born in our solar family. It was a traveler from deep space. In that instant, the calendar became critical. Humanity had only a few months to prepare before the object reached perihelion and then vanished forever. The countdown had begun. From July through late September, excitement grew. Observatories across the world reallocated telescope time. Proposals were drafted to capture its spectrum, its brightness curve, and its every possible nuance. NASA's orbiters at Mars MRO, MAVEN, were included in planning, because Mars's position in early October offered a vantage point Earth could not match. Meanwhile, amateur astronomers joined the chase, eager to track the third interstellar object ever found. By late September, the atmosphere was charged with anticipation. The stage was set for October, the month when 3I divided by Atlas would enter prime view. But here, the timeline bent under politics. On September 30th, Congress failed to pass a funding bill. At midnight, the US government shut down. On October 1st, NASA's public communication was frozen by law. And on that same date, the 3I divided by Atlas Mars window opened. Science said go, politics said pause. That overlap created the infamous dead zone, a week when instruments almost certainly recorded, but the outside world heard nothing. From October 17, 2024, the silence was total. Forensic analysis shows the data pipeline likely still functioned internally. Spacecraft continued operations, telemetry was stored, but public-facing channels went dark. The effect on perception was dramatic. When placed in isolation, this 7-day gap looks like erasure, but when aligned with the fiscal calendar, it looks like bureaucracy. Two unrelated clocks, the cosmic and the political, struck the same hour, and the result was absence. This is the first gift of the timeline: perspective. Seeing events in order drains them of some mystery, yet perspective does not erase emotion. The public had waited since July for this very week. When nothing came, suspicion bloomed. That is why clarity must be paired with patience. Discovery unfolds across months, not days. The story of 3I divided by Atlas could not be told on October 7th. It required waiting through perihelion at the end of the month, and then through conjunction before the object re-emerged in November and December. So the first segment of the timeline delivers both explanation and unease. It tells us why silence fell, but also why it stung. Clarity shows us the sequence. Patience reminds us that the sequence is not complete, and only by following the line all the way forward can we hope to replace suspicion with understanding. If July and September marked discovery and anticipation, October was the crucible. To understand the weight of this month, we must separate it into 3 key phases: the dead zone of early October, the perihelion window of late October, for the post-perihelion silence that followed. Placing them on a clean timeline strips away some of the drama, while also highlighting why patience is required to make sense of the story. The first phase, already infamous, was the October 17 dead zone. During this stretch, Mars held its prime observational advantage. NASA orbiters were in position, amateur astronomers on Earth strained through solar glare, and global attention peaked. Yet, government shutdown protocols sealed the public pipeline. From the outside, the week is a blank. From the inside, raw data almost certainly accumulated in mission archives. The emotional sting is real expectation met silence, but the timeline shows the overlap was caused not by choice, but by circumstance. The second phase came 3 weeks later. On October 29-30, 2024, 3I divided by Atlas reached perihelion, its closest pass to the Sun at about 1.36 AU. Perihelion is always the moment of truth for comets and interstellar objects. Heat peaks, outgassing surges, brightness fluctuates, small jets of gas can alter orbits, creating the perturbations scientists chase as clues to composition and structure. But from Earth, perihelion coincided with poor viewing geometry. The object's elongation from the Sun was low, meaning it was drowned in glare. Ground-based telescopes caught only fragments. Space-based instruments fared better, but their capacity was limited. Again, the timeline reveals why little public data appeared: physics and geometry, not secrecy. The third phase is less glamorous but equally important: the post-perihelion silence of November 2024. After perihelion, 3I divided by Atlas moved behind the Sun relative to Earth, entering what astronomers call solar conjunction. During conjunction, communication with the spacecraft is risky, and observations from Earth are nearly impossible. This phase, too, was always going to be a blind spot. No amount of agency politics could change the geometry of orbits. The comet was simply hidden by the Sunday. The timeline makes this obvious. The absence of data in November is not a puzzle, it is orbital mechanics at work. Seen in sequence, October and November look less like deliberate withholding and more like inevitability. Bureaucracy created one gap, geometry created another. Together, they bookended perihelion with silence. To the impatient, this feels intolerable. To the forensic eye, it is explainable. The story of 3I divided by Atlas is not a headline, but a process. Detect in July, plan in August, lose access in October, wait in November, re-emerge in December. That slow unfolding is not suspicious. It is the nature of astronomy. The second lesson of the timeline, then, is the virtue of Qian-yun. Events unfold according to physics and policy, not according to our hunger for immediacy. Discovery is not a sprint, it is a sequence. By tracing that sequence, we replace the question, why silence, with the answer, because that is when silence is unavoidable. And in that answer lies reassurance. If November was the blind spot, then December became the moment of return. As Earth's line of sight cleared from the sun's glare, telescopes once again locked onto 3I divided by Atlas. This was the final phase of the 2024 timeline: reappearance and review. Forensic chronology reminds us that only by waiting through this cycle could scientists assemble a complete picture. In early December, amateur astronomers in both hemispheres began reporting the comet faintly in the dawn sky. Soon, professional observatories joined in, capturing spectra and light curves once again. Mars orbiters, too, resumed routine science campaigns, and their data began trickling into public channels as funding stabilized and shutdown protocols lifted. Suddenly, the silence of October and November looked less like a void and more like an intermission. The story had not ended. It had simply paused. This is where patience proves its worth. A timeline shows us that absence was always temporary. What seemed like a blackout in October was balanced by fresh data in December. What looked like erasure became, in retrospect, a delay. Science is cumulative. The dots from July, October, and December, when connected, reveal an arc that no single point could show. By tracing the whole, we see 3I divided by Atlas, not as a mystery hidden, but as a visitor documented in stages. And yet, the psychological lesson is equally important. Silence, even temporary, reshapes perception. Many who followed the story in real time will always remember October 2024 as the month of nothing. Their memory timeline ends there, colored by frustration. Only those who extend their patience into December see the fuller arc. This is why communicating timelines matters. Without clarity, gaps breed suspicion. With clarity, gaps become part of the process. The final value of the timeline is that it restores proportion. 3I divided by Atlas was never a single-week story. It was a 5-month narrative: July discovery, September anticipation, October silence, November conjunction, December re-emergence. Each stage had reasons, each stage had consequences. Plotted together, they replace drama with discipline. They remind us that astronomy is not about instant gratification, but about waiting for orbits to align and data to return. So the clarity of Part 7 is this: the sequence itself is the explanation. The silence was not sinister. It was scheduled by both law and geometry. The return was not miraculous. It was inevitable by physics. The lesson is not to rush to judgment in the middle of the story, but to wait for the story to unfold. With 3I divided by Atlas, patience was not just a virtue, it was the only way to see the whole truth. Speculation spreads like wildfire, but evidence moves at the pace of discipline. In the unfolding story of 3I divided by Atlas, that contrast has never been more visible. One ignites instantly, fueled by imagination. The other takes time slower, steadier, painstakingly verified until it is ready to stand. To mistake one for the other is to mistake noise for signal. And in the case of an interstellar visitor, mistaking the two can mislead an entire generation. By October 2024, speculation was running ahead of facts. The government shut down, and the poor observing geometry around Mars created silence at the very moment anticipation peaked. Into that silence rushed theories. Perhaps 3I divided by Atlas was maneuvering, perhaps its orbit defied Newton, perhaps NASA was hiding unusual data. None of these claims rested on hard numbers, they were built from absence. And absence, history shows, is fertile soil for conspiracy. The less we know, the more stories we invent. But science does not rest on invention, it rests on verification. A hypothesis is not the same as a headline, it is a question waiting to be tested. This distinction is critical because speculation feels satisfying. It delivers instant closure. Evidence feels frustrating. It requires patience, uncertainty, and sometimes months of waiting. Our brains crave quick answers, so when official voices fall quiet, we create our own. That is why speculation spreads faster. Psychologists point to confirmation bias, our tendency to seek patterns that confirm what we already believe. If someone expects NASA to hide information, every delay feels like proof. If someone expects interstellar objects to be mysterious, every silence looks like confirmation. The mind leaps ahead, often leaving evidence behind. Here is the danger. Speculation can harden into belief. Once a claim takes hold, say, that 3I divided by Atlas shifted course unnaturally, later data struggles to dislodge it. Psychologists call this belief perseverance. First impressions become sticky. This is why discipline is not optional. Without skepticism, every gap becomes an alien narrative, every bureaucratic pause becomes a cover-up, and in that rush, we risk missing the extraordinary when it actually occurs. The forensic path is clearer. Always ask 3 questions. What do we know? How do we know it? What do we not yet know? Applied to 3I divided by Atlas in October 2024, the answers are straightforward. Asterisk. We know its orbit is hyperbolic, eccentricity above 1, confirmed by multiple independent teams. Asterisk. We know it passed near Mars at to 30 million kilometers, too far for resolution. Asterisk. We know perihelion occurred on October 2930 at 1.36 AU. Asterisk. We do not yet know its exact rotation, composition, or outgassing profile. That final category not yet known is where speculation thrives. But it is also where discipline must step in. To remain patient in uncertainty is not weakness, but strength. In the courtroom of science, absence of evidence is not evidence of absence, nor is it proof of anomaly. It is simply the signal to wait. So the first lesson of speculation versus evidence is this. A communication gap is not proof of conspiracy. A delay is not the same as deception. Extraordinary claims demand extraordinary proof. Until that proof arrives, clarity means saying, we do not yet know. That answer may be unsatisfying, but it is the foundation of credibility, and the only way to ensure that when true anomalies appear, they will be recognized for what they are. If speculation spreads faster than evidence, the question becomes, how do we discipline ourselves to wait? The answer lies in method, what we might call the scientific toolkit. Without it, every delay feels like a void to be filled. With it, delays become part of the process. The first tool is source scrutiny. Ask not only what is being claimed, but who is making the claim. Is the source a peer-reviewed team publishing orbital solutions, or is it a social media account extrapolating from blurry images? With 3I divided by Atlas in late 2024, credible information came from minor planet center circulars, NASA updates once operations resumed, and observatories logging astrometry. Everything else, while potentially interesting, lived in the realm of speculation. By separating source from noise, we impose discipline on ourselves. The second tool is distinguishing prediction from confirmation. Predictions are models, they tell us what should happen if our physics is right. Confirmations are data points, they tell us what did happen. The two should be compared, not conflated. During October 2024, models predicted small non-gravitational perturbations near perihelion, but until observations after October 29 were processed, those remained predictions, not proof. Social chatter blurred the line, treating might as did. The toolkit reminds us, until data is confirmed, it is provisional. The third tool is context awareness. Science rarely happens in isolation. Data gaps may come from geometry, funding cycles, or simple weather on Earth. To treat those gaps as evidence of suppression is to ignore context. The dead zone of October 17 was frustrating, but context shows it was shaped by the shutdown law. November's silence was shaped by solar conjunction. Context reframes absence as expected, not suspicious. This awareness tempers speculation with patience. The fourth tool is the burden of proof. In logic, the extraordinary claim carries the heavier weight. If someone argues that 3I divided by Atlas altered its orbit unnaturally, the burden rests with them to present extraordinary evidence, clear, repeatable, peer-reviewed. A single anomaly, stripped of error bars or calibration notes, cannot overturn centuries of orbital dynamics. The toolkit reminds us to assign weight appropriately. Claims without evidence deserve curiosity, not belief. Together, these tools create what might be called a discipline of waiting. Waiting is not passive, it is an active restraint. It is saying, I will not accept a claim until it passes the filter of sources, predictions, context, and burden. This restraint protects not only truth but also wonder, because when evidence finally arrives, say, when December 2024, observations confirmed 3I divided by Atlas, was still hyperbolic, despite minor perturbations, we can trust the result. It is no longer a rumor, it is reality. This is where the Keu Goiki Lut Kwa Hoc becomes urgent. The public must learn to resist the instant pull of speculation, and scientists must model that restraint. When NASA says, we do not yet know, it should be heard not as evasion, but as integrity. When amateur data appears, it should be seen not as definitive, but as provisional. This culture of patience is hard to build in an age of viral speed, but without it, science risks losing control of its own narrative. So, the second lesson of speculation versus evidence is this. Discipline is the shield against distortion. Without discipline, every silence breeds fantasy. With discipline, silence becomes part of the timeline. And in that timeline, truth is not lost, it is only delayed. If discipline is the shield, then evidence is the sword. The story of 3I divided by Atlas proves that the only way to cut through rumor is with data hard, repeatable, transparent. And in December 2024, as the comet emerged from behind the sun, the sword began to swing. Fresh astrometry confirmed that 3I divided by Atlas remained on a hyperbolic path. Minor deviations were detected, consistent with low-level outgassing near perihelion, but nothing suggested exotic propulsion or deliberate maneuvers. Spectral analysis revealed signatures consistent with volatile ices, though still unusual compared to most comets. Photometric curves suggested slow rotation, not chaotic tumbling. Each new data point was modest, but collectively they painted a clear picture. 3I divided by Atlas was extraordinary, not because it broke physics, but because it confirmed them, because it reminded us that the same laws hold even for travelers from another star. And yet, speculation did not vanish. Some clung to early theories, insisting that the anomalies were edited out. Others shifted the goalposts, suggesting the very act of releasing data in December was itself proof of manipulation. This is the enduring power of speculation. It adapts. Evidence may answer questions, but speculation always invents new ones. The challenge, then, is not only producing evidence, but cultivating the discipline to recognize when enough evidence has spoken. This is why scientific patience must be paired with public communication. If silence is left unexplained, speculation fills it. If data is released without context, misinterpretation warps it. The balance is delicate. Agencies must not only collect evidence, but also narrate the process, reminding the public that science is not instant revelation, but stepwise accumulation. Without that narration, the discipline required feels like neglect. With it, patience feels like participation. The deeper lesson is cultural. In an age of speed, science must defend slowness. The methodical pace of peer review, calibration, and error checking is not a flaw, it is the feature that makes science trustworthy. The wildfire of speculation burns bright but leaves ashes. The slow growth of evidence builds structures that endure. Choosing between them is not just a matter of curiosity, it is a matter of credibility. So what does the timeline of 3I divided by Atlas teach us about speculation versus evidence? That silence is not always sinister. Those gaps are not always proof. That anomalies must survive the full discipline of verification before they can be called extraordinary. Most of all, it teaches us that wonder and patience are not opposites. To wait for evidence is not to kill curiosity, but to preserve it until it can be satisfied truthfully. In the end, 3I divided by Atlas will leave the solar system forever, fading into interstellar night. Speculation will chase it, as it chased Oumuamua before, but the evidence we gather, slow, careful, disciplined, will remain. And it is that evidence, not the wildfire of rumor, that future generations will inherit. The final lesson of Part 8 is simple but demanding. Believe in evidence, not immediacy. Let speculation spark curiosity, but let discipline shape belief. Because in science, patience is not the enemy of truth, it is the only path to it. Two agencies watched the same comet, but spoke in very different voices. As 3I divided by Atlas swept through its Martian window in early October 2024, the European Space Agency released steady updates while NASA fell into mandated silence. Same sky, same science, yet two radically different approaches to communication. The contrast was not just procedural, it became symbolic, a mirror of how institutions shape public trust. To understand this divergence, we begin with culture. ESA operates in a European framework where openness is expected as part of public service. Member states fund their missions, and those governments expect timely returns in the form of data and updates. ESA scientists often release preliminary spectra, brightness curves, and even raw imagery with clear caveats. They assume their audience can handle uncertainty as long as the flow of information continues. This creates a rhythm of trust. Small, steady disclosures that show the process unfolding in real time. NASA, by contrast, functions within a system far more entangled with politics. It is a federal agency, funded through appropriations subject to congressional negotiation. Every communication can be passed by lawmakers, watchdog groups, or international partners. That pressure creates caution. When the US government shuts down, NASA must legally halt non-essential activity, including science updates. The Anti-Deficiency Act makes this a matter of compliance, not discretion. Even when orbiters gather valuable data, the pipeline to the public closes. The culture here is shaped not by scientific instinct, but by legal guardrails. This became vivid in October 2024. ESA's Solar and Heliospheric Observatory, though operating under its own constraints, continued to release graphs of solar wind data relevant to 3I divided by Atlas. It noted faint signatures, explained low solar elongation, and emphasized the limits of visibility. But still, the updates came. Even small disclosures reassured the public that the process was transparent. NASA's Mars Reconnaissance Orbiter and MAVEN almost certainly collected similar telemetry, yet their output remained locked in databases, invisible until the shutdown lifted. The raw reality was the same: signals faint, resolution low, but the perception diverged completely. The key frontage here is that this divergence was not about intent, but about systems. ESA is built to default toward disclosure. NASA is built to default toward caution. One frames science as a steady conversation, the other as a polished report delivered when safe. Both approaches have logic, but when viewed side by side during a once-in-a-lifetime event, the result felt jarring. Transparency looked like honesty, silence looked like secrecy. The emotional effect cannot be ignored. For European observers, ESA's modest updates maintained connection, even if the data was not dramatic. For American audiences, NASA's silence created a vacuum. Into that vacuum rushed speculation, suspicion, and frustration. The contrast fueled online debates. Why can Europe speak while America stays quiet? What is NASA hiding? In truth, NASA was hiding nothing, it was obeying the law. But perception, not procedure, drives trust. So the first lesson of this timeline is cultural. ESA communicates within a framework of openness, NASA within a framework of restraint. Neither culture is inherently superior, each reflects its political environment. Yet when placed in parallel during an interstellar visitation, the difference became more than bureaucratic. It became psychological. People began to project meaning onto silence, and in that projection, the story of 3I divided by Atlas turned from science into a symbol. Understanding this cultural divergence is the first step toward clarity. The comet itself did not change. What changed was the way two institutions narrated or withheld their story. And that narrative difference may shape public memory of 3I divided by Atlas as much as the data ever will. If culture explains part of the divergence, politics and law explain the rest. To see why ESA could speak while NASA stayed silent, we must trace the frameworks that governed them in the autumn of 2024. In Europe, ESA is funded by contributions from multiple member states, each expecting shared returns. Its mandate emphasizes openness as a demonstration of value. Reports, images, and even preliminary findings are framed as proof of public investment. While ESA scientists remain cautious about overinterpretation, they are encouraged to communicate frequently. Openness is written into their legitimacy. When 3I divided by Atlas crossed its October window, ESA had the freedom and the expectation to share what it could, even if the data was thin. NASA, meanwhile, sat within the machinery of Washington. The U.S. government shutdown on September 30th, 2024, triggered the Anti-Deficiency Act, a law designed to prevent unauthorized spending. Under this law, NASA could continue essential functions, keeping spacecraft safe, monitoring astronaut life support, but not non-essential activities like public updates. In other words, the data pipeline did not stop flowing, but the public-facing valve was legally shut. Even if engineers and scientists wanted to post light curves or raw frames, they were prohibited. Silence was mandated, not chosen. The effect of these frameworks was magnified by timing. ESA's updates came exactly when anticipation peaked, in early October. NASA's silence arrived in the same week, precisely as the comet passed Mars. From a procedural standpoint, the overlap was a coincidence. From a perceptual standpoint, it was devastating. The side-by-side contrast suggested intentional secrecy in America versus candor in Europe. In reality, the agencies were obeying different rulebooks. Here, the font-itch must be sharpened. ESA's openness is not an absolute virtue. NASA's silence is not an absolute flaw. Each strategy has risks. ESA risks releasing preliminary data that could later be corrected, potentially undermining credibility. NASA risks fueling conspiracy by saying nothing until results are polished. The balance is delicate. But in October 2024, the optics were stacked against NASA. When one agency spoke and another did not, the public interpreted motive instead of context. There is also the political climate to consider. In Europe, science communication is less entangled with partisan battles. In the US, NASA's every move is scrutinized by Congress, where funding is debated line by line. Agency leaders know that premature or misinterpreted announcements can trigger hearings, budget fights, or international embarrassment. Silence is safer, even if costly to public trust. That political reality explains much of the restraint. It is not that NASA scientists lack the will to speak. It is that the institutional risk of speaking outweighs the benefit. This is where empathy becomes necessary. It is easy for the public to say, why not just share? But inside NASA, every release carries liability. Engineers and scientists know their careers, and sometimes their missions, depend on protecting the agency's credibility. Their silence is not disrespect for the public. It is self-preservation within a legal and political environment. ESA does not face the same pressures, so its voice sounds freer. The comparison, then, is not about which agency cares more about science. It is about how different systems reward or punish communication. Europe rewards steady openness. America punishes missteps more harshly. Put those systems side by side during an interstellar event, and the public sees contradiction where there is only contrast. This second layer of analysis, political and legal, shows us why two agencies studying the same comet spoke so differently. It was not about the comet at all. It was about their rulebooks, and rulebooks, not telescopes, decided who spoke and who stayed silent. If culture shaped the tone and law dictated the pace, the final piece of the comparison is consequence. How did the public respond to ESA's transparency and NASA's silence? And what can agencies learn from that divergence as humanity prepares for the next interstellar visitor? For Europe, the consequence was modest but positive. ESA's updates did not dominate headlines. They were technical, incremental, sometimes dry. But they built a record of continuity. Each release, even when it reported faint detections or limited resolution, reinforced the sense that the process was unfolding in public view. Trust was not created by spectacle, but by presence. Europeans following 3I divided by Atlas felt included in the story, even when the story was mostly caveats. This presence mattered. It created a baseline of credibility that will carry into the next event. For NASA, the consequence was sharper. Silence in October 2024 created an information vacuum at precisely the wrong moment. Into that vacuum flowed speculation. Was the comet maneuvering? Was the data suppressed? Why could ESA share while NASA could not? Rational explanations, shutdown law, political caution, classification, protocols struggled to compete with the emotional immediacy of absence. By the time December updates resumed, much of the narrative had already been shaped by suspicion. NASA's evidence was real, but the story was already bent. Here lies the lesson. Transparency is not only about data, it is about timing. A faint spectrum released in October may not have changed the science, but it would have changed perception. It would have signaled presence. Even a simple statement, data is being collected but cannot be shared until operations resume, might have eased doubt. Silence without context is louder than any conspiracy. This is where Thongkam and Kuyen come together. NASA scientists are not villains. They were bound by law and politics, caught between compliance and communication. Yet the comparison with ESA shows that rules can be re-examined. Could exceptions be carved out for rare interstellar events? Could minimal placeholder statements be allowed during shutdowns? Could joint coordination with international partners ensure that some flow of updates continues, even when US agencies are silenced? These are questions worth asking, not to assign blame, but to prepare for the future. The public deserves clarity, but agencies deserve understanding too. ESA's transparency works because its system rewards it. NASA's silence happens because its system punishes risk. Recognizing this distinction prevents cynicism. It reminds us that institutions are products of environments, but recognition should not lead to resignation. Systems can adapt, cultures can evolve, rulebooks can be revised when the stakes are high enough. The comparative story of October 2024 is not about one agency being right and the other wrong. It is about how different frameworks create different optics. ESA built trust through small disclosures. NASA lost trust through unavoidable silence. Both studied the same comet. Both gathered valuable data. Yet the way they spoke or did not speak became part of the legacy of 3I divided by Atlas. So the final recommendation is simple but profound. Communication is as critical as observation. Telescopes collect photons, but agencies shape meaning. If silence breeds speculation, then even minimal transparency is an investment in trust. The next interstellar object will arrive sooner or later. When it does, the memory of 3I divided by Atlas will remind us that openness is not a luxury. It is part of the science itself. The real test of 3I divided by Atlas is not what happened before the silence, but what happens after it re-emerges. The weeks before the conjunction were full of anticipation, speculation, and frustration. But astronomers knew all along. The decisive evidence would come only after the comet cleared the sun's glare and reappeared in the night sky. That is when predictions meet reality, and when normal can finally be separated from not normal. To understand why this moment matters, we need to revisit the conjunction itself. In November 2024, 3I divided by Atlas slipped behind the sun as seen from Earth. During conjunction, telescopes cannot safely point too close to the sun, and spacecraft risk radio interference. Observations all but stop. It is a natural blackout, dictated by geometry rather than politics. For several weeks, the comet was invisible to us, a traveller behind the curtain. The world waited. The re-emergence in December became the critical checkpoint. By then, astronomers had precise models predicting where the comet should appear, how bright it should be, and what its orbital path should look like. These models included allowances for ordinary perturbations, gas jets, radiation pressure, and gravitational nudges. In other words, normal was already defined. Anything within that range would confirm physics as we know it. Anything outside would raise eyebrows. So, what does normal look like in practice? It looks like a faint dot reappearing roughly where predicted, within arc-seconds of expectation. It looks like brightness levels that match cooling after perihelion, slightly dimmer, but consistent with the behavior of known comets. It looks like the spectra are dominated by volatile ices and dust, familiar signatures of cosmic chemistry. None of this is dramatic. None of it makes headlines. But it is the quiet confirmation that our models hold. And what would be not normal? If the comet failed to reappear at all, despite predictions, if its orbit shifted beyond what jets of gas could explain, if its brightness jumped unpredictably, fading too quickly, or surging when no heating justified it, if the spectra showed elements entirely unexpected, these are the red flags. They do not automatically mean something extraordinary, but they demand forensic attention. Scientists treat them like anomalies in an investigation, document them, test them against error sources, and only after rigorous review decide whether they defy explanation. This is where Qianjun comes in. The public craves instant answers. If 3I divided by Atlas appeared even slightly off, headlines would scream not normal. But science cannot move at that speed. A positional offset might be a calibration issue. A brightness surge might be dust contamination. A spectral blip might be detector noise. Only by collecting multiple independent observations, different telescopes, different instruments, different analysts can scientists decide what is truly out of bounds. That process takes days, sometimes weeks. The discipline is slow, but it is the only guardrail against false alarms. Thus, the first lesson of the post-conjunction test is clear. Not normal must be defined carefully, not emotionally. It is not about surprise. It is about deviation beyond explanation. And that definition requires patience. Patience to let data accumulate, to let errors cancel, to let models be tested. Without patience, every flicker becomes a fire. With patience, true anomalies emerge, clearly, stripped of noise. If the first step is defining normal in advance, the second step is applying that definition with forensic discipline once observations resume. December 2024 provided the stage for this application. As telescopes regained visibility, the comet's reappearance allowed astronomers to measure, compare, and decide whether its behavior fit predictions or fell outside. This process is not glamorous. It is statistical, patient, and often anticlimactic. But it is the bedrock of separating evidence from illusion. The immediate question after the conjunction was orbital accuracy. Teams worldwide checked whether 3I divided by Atlas appeared within the positional error ellipse predicted in October. If the dot fell inside that ellipse, the verdict was normal. If it landed outside by more than the margins allowed for gas jets or solar radiation, it was potentially not normal. This kind of test is simple in principle but hard in practice. Telescopes must calibrate precisely. Atmospheric interference can skew results, and faint magnitude makes pinpointing the centroid of light tricky. That is why single observations are never enough. Multiple teams across continents must compare notes before anyone can call deviation. The second checkpoint was brightness. After perihelion, comets typically dim as they move away from the Sunday models forecasted that 3I divided by Atlas should fade by a predictable factor week by week. Photometric curves were plotted in advance. In December, the test was whether reality matched the curve. If the comet dimmed faster than expected, one possibility was fragmentation pieces, breaking off and dispersing light. If it dimmed more slowly, perhaps it retained volatile ices longer than assumed. Either case might still be natural, but if brightness behaved erratically, surging up without solar justification, that crossed into the not normal zone. The third checkpoint was the spectrum. Instruments analyzed the wavelengths of light to identify gases and dust. Water vapor, carbon monoxide, and carbon dioxide are standard. Sodium and other metals sometimes appear. For 3I divided by Atlas, the baseline expectation was a composition broadly consistent with other long-period comets, perhaps with subtle differences due to its interstellar origin. What would count as not normal? The detection of compounds that do not fit cometary chemistry, unexpected industrial-like ratios, for example, or a spectral profile too smooth, suggesting reflection rather than emission. These are rare, and no credible team jumps to conclusions without exhaustive checks. But they are on the list of watch for this. Throughout December, scientists urged patience. Headlines speculated wildly on any early deviation, but within the community, caution prevailed. An offset in orbit might be traced to underestimated outgassing. A brightness anomaly might vanish once background stars were subtracted correctly. A spectral blip might be detector noise. This is why agencies and journals insist on replication. A finding is not normal until it survives every attempt to explain it away. For the public, this process can feel like a delay, but in truth, it is discipline. The temptation to label every surprise as an anomaly is strong, especially with an interstellar object. Yet anomalies are only meaningful when they resist explanation. Patience ensures that science does not mistake error for signal. Without patience, we would declare every irregularity extraordinary. With patience, we discover which irregularities actually matter. So the second lesson of the post-conjunction test is this. Applying the definition of normal requires not just measurement, but replication. It is not enough for one telescope to see a flicker. Many must see it, under different conditions, before it is declared real. Only then does not normal enter the record, and only then can it shape how we understand what visited us from beyond the stars. If December was about measuring whether 3i divided by Atlas reappeared, as expected, January 2025 and beyond were about interpretation. This is the stage where science distinguishes between not normal, that is simply unusual, and not normal, that is truly extraordinary. The difference lies not in imagination, but in discipline. Once positional, photometric, and spectral data were collected, the task shifted to modeling. Astronomers ran simulations, feeding in every known variable: solar radiation pressure, gravitational perturbations, cometary outgassing. They tested whether deviations observed in December could be explained within this framework. Most of the time, they could. A slight orbital offset, likely due to asymmetric gas jets. A slower dimming curve, possibly more ice beneath the surface. A spectral surprise, sometimes calibration error, sometimes dust scattering. This is the normal cycle. Apparent anomalies are gradually absorbed into known physics. But what about the deviations that resist absorption? This is where the definition of not normal sharpens. If, after weeks of analysis, a measurement still cannot be reconciled with models, if an acceleration persists that no gas jet explains, or if a spectral line appears that no chemistry predicts, then the anomaly graduates from curiosity to candidate. At that point, scientists cautiously describe it as unexplained. They do not leap to conclusions, but they do mark it as significant. This is how discovery advances, not by mistaking every noise for signal, but by identifying the rare signals that endure scrutiny. Here, policy guardrails play an important role. Agencies like NASA and ESA know that premature announcements can do more harm than good. Declaring something not normal too early invites sensational headlines that are nearly impossible to retract later. That is why official channels often sound conservative, even underwhelming. Their language is careful by design. The guardrail exists to protect credibility, ensuring that when something is labeled anomalous, the word carries weight. For the public, this conservatism may feel frustrating. For the scientific process, it is essential. The patience required here cannot be overstated. Months may pass between raw detection and final interpretation. During that time, speculation continues online, often declaring anomalies long before evidence is ready. Yet history shows the wisdom of waiting. Oumuamua's odd acceleration, once thought potentially artificial, is now better explained by natural models of outgassing and shape. Borisov's unusual chemistry, initially puzzling, has been integrated into our understanding of interstellar comets. Each case demonstrates that anomalies shrink under patient analysis more often than they expand into mysteries. So, what would be truly not normal for 3i divided by Atlas? Not a delay in data. Not a faint reappearance. Not a curve slightly off projection. Truly not normal would mean a sustained, replicated deviation that survives every known explanation. That threshold is high, deliberately so, because only anomalies that clear that bar can justify reshaping our understanding of physics or entertaining more radical possibilities. The final lesson of the post-conjunction test is thus one of discipline and patience. Not normal is not defined by surprise or speculation. It is defined by persistence against scrutiny. Until then, the most rational stance is restraint. Let the data accumulate. Let the models be tested. Let time do its work. Only then can we tell whether 3i divided by Atlas is simply another strange but natural traveler, or a messenger that forces us to rewrite the laws we thought we knew. In the story of 3i divided by Atlas, the silence of science collided head-on with the noise of media. For weeks, telescopes collected faint signals quietly, but newspapers and social feeds demanded spectacle. The result was a widening gap, the pace of evidence lagging behind the pace of headlines, the patience of scientists colliding with the impatience of the audience. To understand why this gap matters, we need to analyze not only science but psychology. Public expectation operates on its own clock. From the moment 3I divided by Atlas was identified as interstellar in July 2024, the label itself triggered imagination. Interstellar is not just a category, it is a magnet for wonder, fear, and speculation. People immediately connected it to Oumuamua and Borisov, to old debates about alien probes, to Hollywood imagery of messengers from the stars. The emotional charge was instant. By the time October arrived, the public had been primed for something extraordinary. This priming created what psychologists call anticipation inflation. Every day without an update felt longer than it really was. A week of silence in early October felt like a month. By mid-October, frustration had already bloomed. The shutdown amplified it, but even without politics, the geometry of conjunction guaranteed blackout periods. Few outside astronomy knew this. Instead, they interpreted silence as absence, or worse, concealment. The expectation gap is not irrational. It is human. People want to feel part of discovery. They want images, narratives, milestones. They want closure. Science, by contrast, offers uncertainty, caveats, and slow accumulation. This mismatch creates tension. When the object went behind the sun in November, scientists accepted the blackout as normal. Many in the public, however, saw it as intolerable. Their expectation had been built by months of hype, and the quiet felt like betrayal. So the first analytic point is this: public expectation is not shaped only by science, it is shaped by cultural narratives, by past experiences, and by psychological hunger for meaning. With 3I divided by Atlas, the interstellar label carried weight far beyond its technical definition. It promised something extraordinary, and when communication faltered, that promise turned into pressure. Understanding that psychology is the first step to bridging the gap between evidence and expectation. If public expectation is the demand side, media dynamics are the supply side. And during the 3I divided by Atlas window of 2024, the supply and demand reinforced each other in a cycle that often left science squeezed in the middle. Modern media does not reward patience, it rewards immediacy. The attention economy pushes headlines that are fast, dramatic, and emotionally charged. A headline reading, "NASA waits for more data," earns little traction. A headline reading, "NASA goes silent as comet nears Mars," spreads rapidly. The difference is not in accuracy but in framing. And in October 2024, framing was everything. Television news segments highlighted the silence as suspicious. Social platforms turned minor details into viral claims. A faint magnitude variation became proof of artificial control. A scheduling delay became cover-up. The compression of time where every hour feels like a crisis update created pressure on scientists to respond at a pace that evidence could not support. This mismatch is structural. Journalism seeks fresh angles daily. Science produces clarity monthly, sometimes yearly. Between those tempos, distortion grows. Another dynamic was narrative simplification. Science thrives on nuance error bars, caveats, probabilities. Media thrives on binaries: normal versus not normal, discovered versus hidden. When ESA released modest updates, headlines exaggerated them into "Europe reveals what NASA hides." When NASA complied with the shutdown law, headlines framed it as deliberate silence. The nuances of procedure, geometry, and calibration were flattened into storylines designed to maximize engagement. It would be unfair to blame the media entirely. Journalists also face public pressure. They must serve audiences hungry for closure, not footnotes. But without deeper literacy, the cycle can corrode trust. Each simplified headline leaves the impression that agencies are withholding, when in fact they are often constrained by law or physics. Each viral claim makes patience harder, feeding a loop in which silence feels like secrecy and speculation feels like truth. Forensic analysis shows how this loop formed around 3I divided by Atlas. Public expectation primed suspicion. Media dynamics amplified it with framing. The result was a narrative where silence seemed louder than evidence. Understanding this loop is crucial because it will repeat with every rare cosmic visitor unless the cycle itself is recognized. So the second analytic point is this: media dynamics compress time and flatten nuance. That distortion does not mean bad faith, but it does mean misalignment. Science must navigate not just data, but the storytelling economy that interprets it. Without conscious correction, every future interstellar object risks becoming another case study in how media noise outpaces scientific signal. If the first two layers are psychology and media, the final layer is consequence. What happens when public expectation and media dynamics collide with the slower pace of science? The answer is not just noise, it is erosion of trust, unless managed with care. The 3I Divided by Atlas episode showed this clearly. By December 2024, when post-conjunction data began to flow, much of the narrative had already been shaped. Some in the public dismissed new findings as too little, too late. Others clung to early speculative claims, unwilling to revise their beliefs in light of evidence. This is the danger of the cycle. Once a dramatic frame is set, correction struggles to catch up. Trust gaps widen, and even accurate data feels like an afterthought. But there is also an opportunity. Understanding how expectation and media work allows science agencies to adapt without abandoning rigor. One strategy is preemptive framing. Instead of waiting for silence to be misinterpreted, agencies can announce blackout windows in advance. For 3 weeks during conjunction, no observations will be possible. Expect updates only after December 5. Such framing gives audiences a timeline, turning silence into a scheduled pause rather than a suspicious absence. Another strategy is layered communication. Agencies can offer both technical releases for specialists and simplified summaries for the public, ensuring nuance survives translation. ESA's cautious bulletins hinted at this model. NASA, constrained by shutdown law, lacked that flexibility, but the comparison highlights what might be improved. Even placeholder statements acknowledging delay can maintain trust. Finally, there is the role of media literacy for the public. Viewers and readers must learn to recognize the rhythm of science. Not every gap signals conspiracy. Not every anomaly means a breakthrough. The public deserves transparency, but also needs tools to interpret it. Education in how evidence accumulates slowly, carefully, and often anticlimactically helps align expectation with reality. So the third analytic point is consequence. Unmanaged expectation and distorted media can corrode trust, but managed expectation and proactive communication can preserve it. The story of 3I Divided by Atlas is a reminder that science is not just about telescopes and equations. It is also about narrative, timing, and trust. In the end, the comet itself behaved as comets do, strange but not supernatural. What mattered just as much was how people experienced it. That experience was shaped not only by data, but by silence, by headlines, and by the psychology of waiting. If we want future encounters with interstellar visitors to be remembered for discovery rather than division, we must learn this lesson now. Patience must be paired with communication, and media speed must be balanced with scientific depth. Only then can the public expectation, the media cycle, and the discipline of evidence converge toward clarity rather than conflict. The silence of October was not the end of the record, it was the beginning of a forensic audit. When 3I Divided by Atlas disappeared into the twin gaps of shutdown and conjunction, many assumed the trail went cold. In truth, surveillance never stopped. What paused was the public stream, not the raw watch. The real work began afterward, reconstructing, comparing, and testing what the hidden eyes in space had seen. Space surveillance is broader than astronomy. Telescopes like Hubble or the Very Large Telescope provide scientific images, but an entire parallel infrastructure exists. Radar arrays, defense satellites, sky monitoring networks. These systems are not designed for comets, but they cannot ignore them either. Anything moving across the sky is logged, catalogued, and compared. In October 2024, while NASA's public updates froze, those networks continued recording. Their data was not gone, it was hidden by classification, budget law, or delay. For forensic analysis, the question is not whether surveillance existed. It is whether and when those records surface. After-gap forensics begins with alignment. Once 3I Divided by Atlas reappeared in December, astronomers compared open data from telescopes with fragments of tracking data that trickled out later. The method is systematic. Asterisk. Step 1. Confirm positional matches did classified records. Align with where open astronomy predicted. Asterisk. Step 2. Confirm. Velocity did trajectory adjustments match known physics, or did they hint at anomalies? Asterisk. Step 3. Confirm, light curve, consistency. Did brightness in defense logs match brightness in civilian photometry? Each step reduces uncertainty. Each step also tests whether silence was just procedural, or whether something had been intentionally redacted. The logic here demands patience. Public audiences expect instant release, but forensic auditors know it takes weeks to stitch timelines. Data often arrives fragmented. A radar blip here, an astrometric coordinate there, a delayed ESA report, a NASA archive upload. Only by collating them across agencies do gaps close. That is why October's silence was not a void but a workload deferred. December was not just observation, it was verification. This framework reframes the hidden. Hidden does not mean absent. It means delayed, encrypted, awaiting clearance. The forensic approach assumes nothing, checks everything, and only then decides. This patience is not passive. It is active skepticism, the discipline of refusing to leap from gap to anomaly without proof. In the case of 3I divided by Atlas, the hidden months became a test. Would the after-gap records close the circle or open new questions? If the first task of after-gap forensics is alignment, the second is interrogation. Every data set that emerges after silence must be tested for integrity. This is where space surveillance data, especially from defense sources, becomes both valuable and controversial. Unlike civilian observatories, military tracking systems are optimized for fast-moving satellites, debris, and potential threats. Their precision is extraordinary, but their transparency is limited. In October and November 2024, such systems almost certainly tracked 3I divided by Atlas as it passed through conjunction. But those logs were not released in real time. Only later, in December and January, did fragments of orbital data appear through indirect channels, summaries, not raw frames. The forensic challenge is to decide, are these summaries consistent, or are they selectively curated? The process resembles a courtroom audit. Investigators ask, does the surveillance data confirm or contradict civilian records? If ESA's December coordinates put the comet within a predicted ellipse, do U.S. strategic command logs when declassified show the same? If not, where is the discrepancy? Could it be explained by methodology, or does it suggest redaction? Each comparison either builds confidence or sharpens questions. The key is never to assume malice or mistake until error sources are fully exhausted. This interrogation phase also covers metadata, dates of release, file formats, and even the order in which observations are published matter. Sometimes, the signal lies not in the numbers but in the delay. If one set of coordinates is withheld for months, forensic reasoning asks why. Was it because of classification cycles, or because the measurement contained an outlier requiring extra review? Again, patience is essential. The slow rhythm of declassification often masks the ordinary process with an aura of secrecy. Only by mapping the timeline of release against the timeline of events can analysts decide if delay equals intent or bureaucracy. Another angle is consistency across nations. Japan's JAXA, Europe's ESA, and independent observatories often release data faster than US agencies, constrained by shutdown law. Forensics compares these records. If brightness recorded in Europe matches radar echoes hinted at in U.S. reports, confidence grows. If gaps remain, suspicion lingers. This is why interagency comparison is so powerful. It strips away single-point dependence and forces anomalies to survive across multiple records. The public rarely sees this slow stitching, but it is here that science protects itself. Without after-gap interrogation, speculation thrives unchecked. With it, anomalies must endure scrutiny, and most do not. Most hidden gaps are eventually filled with ordinary explanations: timing of uploads, calibration delays, clearance procedures. But only by testing them with discipline does the story become complete. Thus, the second layer of after-gap forensics is interrogation, testing data not just for what it shows, but for how, when, and why it was released. In this way, the hidden becomes less mysterious, and patience transforms silence into sequence. If alignment maps the trail and interrogation tests the data, the final step of after-gap forensics is synthesis. This is where fragments, civilian observations, ESA bulletins, defense summaries, amateur logs are woven into a single coherent narrative. The value of this synthesis is not only in proving what happened, but in showing how gaps can be bridged without speculation. For 3I divided by Atlas, the synthesis phase unfolded in early 2025. By then, most December observations had been compiled into peer-reviewed submissions, and defense-related records had trickled out through catalog updates. Analysts lined them up against predictions published before the conjunction. The verdict was methodical. The comet had behaved within expectations. Its orbit showed only minor perturbations explainable by gas jets. Its brightness declined at the modeled rate. Its spectra showed volatile ices, with no exotic anomalies. What had seemed hidden in October was, in retrospect, routine. The silence had not erased evidence. It had only delayed its disclosure. But synthesis is not about closure alone. It is about building resilience for the next event. Every analysis asked, what worked, what failed, what can be improved? Agencies noted that clearer pre-announcements of blackout windows could have tempered public impatience. Media analysts suggested that even placeholder statements, data is being collected, expect review in December, could have prevented runaway narratives. Forensic reviewers recommended more structured pipelines for declassifying space surveillance data, so its value could reinforce, rather than undermine, open science. Patience here becomes policy. To learn from 3I divided by Atlas is to recognize that gaps are inevitable. Geometry, funding, politics, each will create silence again, but silence does not need to mean suspicion. With proper guardrails, it can mean scheduled waiting, understood by both scientists and the public. Forensics reframes the gap as a temporary step in a longer audit, not as a void. That reframing requires communication, discipline, and the humility to accept that discovery is often anticlimactic, but still meaningful. Thus, the final lesson of after-gap forensics is clarity. Hidden does not mean absent, delayed does not mean denied, and patience is not weakness, but the method by which science guards truth. The October silence was dramatic, but the December synthesis was decisive. 3I divided by Atlas left the solar system as expected, its record intact, its anomalies absorbed into physics. The real story was not about secrecy, but about how institutions, surveillance networks, and patient auditors closed the gap. In the end, what matters most is not how loud speculation grew during the silence, but how strong the evidence stood afterward. And that strength came from discipline, aligning, interrogating, and synthesizing until the hidden became history. Every silence exposes a weakness, but every weakness points toward a design that could be stronger. The October blackout during 3I divided by Atlas did not just frustrate the public. It revealed structural capability gaps in how humanity monitors, communicates, and responds to rare interstellar visitors. These gaps are not permanent flaws. They are signals pointing toward new systems we must design if we are to meet the next event with confidence rather than confusion. The first gap was rapid observation handoff. When NASA facilities paused during the October 2024 shutdown, European observatories filled part of the void, but the handoff was clumsy. There was no binding framework to guarantee seamless continuity. Instead, ad hoc coordination meant that observations were duplicated in some cases and missed entirely in others. This left days when the object was certainly visible but poorly tracked. In aviation, redundancy is routine. If one radar fails, another automatically takes over. Space science has no equivalent. 3I divided by Atlas showed us that international astronomy still relies on goodwill rather than structured contingency. A fast response design would formalize that redundancy. Agencies would maintain shared tasking protocols, so if one network pauses, another steps in without delay. The second gap was real-time data processing. Capturing light is only half the job. Converting that light into meaningful coordinates, velocities, and spectra is the harder half. Current pipelines are built for routine science, optimized for accuracy over speed. Data is collected, calibrated, processed, peer-reviewed, and eventually published. For most astronomy, this is enough. For an interstellar visitor, it is too slow. In October, some frames of 3I divided by Atlas sat unprocessed for weeks. A fast response framework would include automated pipelines that reduce data within hours, flag anomalies, and release provisional results. These would not replace peer review, but supplement it, giving decision-makers and the public a first look. Such pipelines already exist in meteorology and seismology, where speed matters. Adapting them to astronomy would close this critical gap. The third gap was communication under constraint. During the shutdown, NASA was legally barred from publishing non-essential updates, but no rule required the agency to announce in advance that silence was coming. The result was a communication vacuum that fueled suspicion. The silence was procedural, but without context, it felt intentional. A fast response design would fix this by establishing continuity statements. Pre-written notices triggered automatically during shutdowns or conjunctions. These would inform the public, data is still being collected, analysis is underway, and updates will resume on a specific date. Even minimal transparency would prevent silence from being mistaken for secrecy. Together, these three gaps, handoff, processing, communication, defined the October blackout. They were not caused by incompetence, but by systems designed for routine, not for urgency. 3I divided by Atlas was the stress test, revealing that the infrastructure of space science has not yet been modernized for fast response scenarios. That diagnosis is not a failure. It is a blueprint. It shows precisely where to build next. So the first analytic layer of capability gaps is clear. We are missing redundancy, automation, and continuity. These are not unsolvable. They are design challenges, problems of architecture that can be fixed with foresight, coordination, and investment. And solving them is not just about avoiding frustration. It is about ensuring that when the next visitor arrives, humanity meets it, not with silence, but with readiness. The October blackout hurt trust. The next time, a fast response system could turn silence into resilience. That shift is not fantasy. It is engineering waiting to be built. If the diagnosis shows us the weak points, the next step is design. Fast response capability cannot just be a slogan. It must be engineered into systems, policies, and workflows. 3I divided by Atlas gave us a blueprint by highlighting what broke down. Now, the challenge is to design what should replace it. The first design principle is redundancy across borders. Astronomy is global, but coordination remains fragile. During the October silence, ESA and smaller observatories tried to fill NASA's absence, but there was no formal mechanism to guarantee coverage. A redesigned system would establish an international task force for interstellar objects. It would function like air traffic control, one central clearinghouse, assigning observational duty across agencies and countries. When one node goes dark, another takes its slot. Such redundancy would transform gaps from random into managed pauses. It would also reduce duplication, ensuring that scarce telescope time is spent efficiently. The second design principle is automation for speed. Human review will always be essential, but the first draft of data does not need to wait for weeks. A fast response pipeline would use algorithms to perform initial reductions, position checks, brightness curves, and spectral line identification. These outputs would be flagged as provisional, but immediately available for cross-checks. For example, if a US observatory goes silent, an ESA telescope could instantly confirm or reject anomalies. Automation would not replace human judgment. It would accelerate it, compressing weeks into hours. Other fields already do this. Earthquake warnings and hurricane forecasts depend on automated early outputs. Astronomy should do the same for visitors from beyond the stars. The third design principle is communication under stress. Silence during shutdown was procedural, but it looked like secrecy. To prevent this, a fast response design must build in default statements. These could be drafted in advance. Data is being collected. Public release will follow clearance. Interim updates may come from partners. Such statements require no new funding or clearance. They are procedural guardrails. Their impact is psychological. They transform mystery into managed delay. The public does not demand constant disclosure. They demand reassurance that silence has a reason. Policy can supply that reassurance with minimal cost. The fourth design principle is simulation before crisis. Agencies train astronauts with drills. Hospitals run disaster exercises. Astronomy rarely rehearses rare object encounters. Fast response design would add simulation protocols. Mock interstellar visitors run through the system to test whether pipelines, handoffs, and communications function under pressure. These rehearsals would expose bottlenecks before real events. They would also train personnel to handle the unique tension of global attention and limited data. 3I divided by Atlas showed what happens when rehearsal is absent. Stress magnifies gaps. Simulation ensures readiness. Taken together, these principles, redundancy, automation, communication, simulation, sketch a framework where capability gaps close. The blueprint is not speculative. Each piece already exists in other fields. What is missing is adaptation to astronomy. That adaptation requires funding, policy change, and international cooperation. But it also requires will. The October blackout should be remembered not only as a frustration but as a wake-up call. It was a stress test that revealed vulnerabilities. Fast response design is the answer those vulnerabilities demand. So the second analytic layer is constructive. We know what failed, and we know how to fix it. The real question is whether institutions will act. Designing resilience is not glamorous. It will not generate headlines like alien probe, but it will build the infrastructure that lets humanity meet the next visitor with confidence. Hope lies not in speculation but in design, and design, once set in motion, can transform silence into readiness. If design principles are the blueprint, the final step is application. A plan only matters when it is built into practice. For fast response systems, that means translating ideals into institutions, budgets, and hardware. The case of 3I divided by Atlas shows how urgent this is and how possible it can be. The first application is dedicated to rapid task assets. Today, most major telescopes run on long-term schedules, booked months in advance. When an interstellar object appears, it disrupts those schedules. That is why the response lags. A solution is to establish a small network of telescopes reserved exclusively for emergency use. These assets would sit idle most of the time, but spring into action the moment a trigger is called, be it an interstellar visitor, a planetary defense alert, or an unusual anomaly. Their cost would be high, but their value would be in responsiveness. 3I divided by Atlas proved how costly delays can be when the sky itself does not wait. The second application is policy bridges across agencies. NASA, ESA, JAXA, and defense organizations all collected fragments of data in October 2024. But those fragments were siloed. Each agency had reasons legal, political, security for withholding. A fast response framework would create standing agreements for limited, provisional data sharing during crises. The principle is simple. Anomalies do not respect borders, so neither should first response science. Drafting these agreements is political work, but the technical infrastructure already exists. Shared platforms can synchronize even provisional data, preventing the vacuum that speculation feeds on. The third application is training for public communication. Silence became damaging not because data was absent, but because explanations were absent. Scientists are trained to analyze, not to narrate. Yet in a global event, narration matters. Training programs could prepare spokespeople to explain why silence occurs, how long it will last, and what the next milestone will be. This is not spin. It is transparency structured for clarity. ESA's modest updates proved that even cautious bulletins preserve trust. NASA's silence proved that, without communication, law-abiding procedures can look like concealment. Training transforms that lesson into readiness. The fourth application is institutionalizing patience. Fast response does not mean instant conclusions. It means instant process. Agencies must make clear. Anomalies will be tested, replicated, and only then announced. This policy clarity prevents premature hype and ensures that, when not normal is declared, it is meaningful. The public deserves both speed and rigor. Fast response design must provide speed of process, not speed of speculation. When these applications are built, dedicated assets, policy bridges, communication training, institutional patience, the next interstellar visitor will meet a world better prepared. The hope lies in construction. 3I divided by Atlas exposed weaknesses, but it also lit the path toward resilience. Silence does not need to mean suspicion. Gaps do not need to mean failure. With design applied, silence can mean structure, and gaps can mean managed waiting. So the final analytic layer of Part 13 is hopeful. Capability gaps are not fatal. They are design opportunities. The October 2024 blackout was frustrating, but it was also instructive. By turning diagnosis into design and design into application, humanity can transform frustration into readiness. The comet has already left us, but the lesson it leaves is still here. Build faster, coordinate better, and communicate clearly. That is how we close the gaps. And that is how we prepare, with hope, for the next messenger from the stars. Trust is not given, it is built, and transparency is not weakness, it is strength. In the story of 3I divided by Atlas, the greatest lesson was not about orbital dynamics or brightness curves. It was about how fragile public confidence becomes when silence collides with expectation, and how it can be reframed into resilience through openness. The comet itself behaved within physics, but the narrative around it escaped control. That gap in trust is as critical to repair as any gap in data. The October 2024 blackout was more than a data interruption. It was a communication fracture. Agencies kept collecting information, but the absence of visible updates left the public to invent their own storyline. In that void, imagination became explanation. Headlines suggested cover-ups, social feeds amplified suspicions, and even reasonable audiences wondered whether something abnormal was being hidden. The truth was simpler: geometry, funding law, and shutdown protocol. But without framing, silence sounded like secrecy. Reframing trust begins with acknowledgement of limits. Agencies do not need to promise what they cannot deliver. They only need to promise clarity about when and why. Saying, "We cannot observe during solar conjunction, updates will resume," December 5 is not weakness, it is credibility. Such expectation setting transforms silence from suspicious into scheduled. People accept pauses when they understand them. They resist pauses when they feel excluded from them. The second foundation is layered communication. Technical bulletins are written for specialists, but the public consumes narratives. Both matter. Without specialist detail, science loses rigor. Without a public narrative, science loses trust. A layered strategy releases the same truth in two forms: peer-level numbers and citizen-level meaning. ESA hinted at this balance in October, publishing modest but steady bulletins. NASA's shutdown silence showed what happens when the layer for the public disappears. The science kept flowing behind the curtain, but the audience saw only darkness. The third foundation is consistency across partners. When Europe shared updates and America went dark, the difference appeared like a contradiction. In reality, each agency was obeying different rules, but perception trumps procedure. To reframe trust, agencies must coordinate not only telescopes but voices. Even a joint placeholder statement, "All partners confirm observation blackout due to geometry. Data expected in December," would have preserved confidence. Consistency is a signal of unity. Disparity is interpreted as deception. Finally, reframing trust requires visible humility. Audiences respond not only to facts, but to tone. Acknowledging uncertainty, admitting gaps, and affirming patience build resilience. People rarely demand instant discovery. They demand honesty about the delay. A short, candid statement often builds more trust than a long, polished silence. The paradox of transparency is that admitting what you do not know often strengthens credibility more than overselling what you do. Thus, the first analytic layer of this part is clear. Trust is built not by perfect knowledge, but by consistent openness. 3. I divided by Atlas was not the story of a hidden anomaly, it was the story of a preventable misunderstanding. Silence without framing frayed trust. Silence reframed as a scheduled pause would have preserved it. The lesson is enduring. Transparency is not an optional luxury. It is part of the science itself, as essential as the telescope lens or the data pipeline. If the first step in reframing trust is acknowledging limits, the second step is building structures that make transparency systematic rather than optional. The lesson of 3I divided by Atlas is not that agencies should share everything instantly. It is that they should create frameworks where communication cannot disappear, even when politics or geometry force observation to pause. One framework is default continuity messaging. Instead of waiting until a blackout happens, agencies can prepare standing scripts, brief statements activated whenever normal updates halt. Imagine if, in late September 2024, NASA had issued a notice: due to US government shutdown protocols, public updates will pause, observations continue. Expect release once operations resume. That single line would have prevented weeks of speculation. Transparency is not about volume, it is about timing. Silence without explanation creates suspicion. Silence with explanation creates patience. A second framework is the shared international voice. ESA's October bulletins and NASA's shutdown silence looked like a contradiction, But contradiction was perception, not reality. Both agencies saw the same comet, both knew the conjunction limited observation, and both collected data. What differed was policy. A reframed trust system would coordinate communication so that partners release aligned statements. Even if data differs in detail, the public hears a unified story. This is a scheduled gap. Here is when to expect more. When transparency is collective, suspicion has no foothold. A third framework is multi-layered translation. Specialists need technical depth, orbital error bars, spectroscopic signatures, magnitude curves. The public needs clarity of meaning. The comet is behaving within expectations. We will know more after December 5. Media needs both. Technical facts to cite, plus a narrative arc to tell. Trust fractures when these layers split, as they did in October. ESA spoke cautiously but continuously, keeping all layers alive. NASA, constrained, lost its public layer. The science was fine, but the perception collapsed. Designing layered releases scientist to media to citizen ensures that one truth reaches all audiences. Finally, a trust framework must include institutional humility. Agencies often fear admitting uncertainty, worried it will be perceived as incompetence. Yet history shows the opposite. When scientists candidly say, "We do not yet know, but we will tell you when we do," credibility rises. The audience does not expect perfection. It expects honesty. 3. I Divided by Atlas taught this in reverse. Silence looked like secrecy, even though it was law. Had agencies voiced that silence with humility, trust would have grown rather than shrunk. Together, these structures, continuity scripts, shared voices, layered translation, visible humility form the architecture of transparency. They are not expensive, they are procedural, but their impact is enormous. They turn pauses into promises, silences into schedules, and uncertainty into honesty. That reframing is what rebuilds trust. So the second analytic layer is constructive. Transparency should not depend on personalities or luck. It should be built into the system, as automatic as the orbit of the comet itself. Because when institutions speak clearly, even in silence, the public does not imagine cover-ups, it learns to wait with confidence. The end of the 3 I Divided by Atlas timeline is not an ending at all. It is a beginning disguised as closure. The comet is already fading into interstellar night, leaving behind only data, memory, and questions. But those questions are not failures of science. They are the fuel of progress. Synthesis means weaving together what we know, confronting what we do not, and promising how we will act when the next visitor arrives. The synthesis begins with clarity. 3. I Divided by Atlas did not break physics. Its orbit remained hyperbolic. Its brightness followed expected curves. Its spectra showed volatiles consistent with known cometary chemistry. What looked extraordinary in silence turned ordinary in hindsight. Yet this ordinariness is not disappointment. It is an affirmation. It proves once again that the same laws stretch from our sun to the stars beyond. The anomaly was never the comet itself. The anomaly was our capacity gap, our struggle to communicate, to coordinate, to sustain trust. From that recognition come open ends. First, the open end of data gaps. October 2024 will always appear as a hole in the observational record. Forensic reconstruction patched much of it, but the scar remains. That scar is instructive. It reminds us that data is not only about telescopes, but about policy, funding, and coordination. If gaps persist, speculation will always fill them. The challenge ahead is not eliminating gaps, they are inevitable, but learning to frame them honestly. Second, the open end of public expectation. The interstellar label will always spark imagination, and silence will always amplify it. No synthesis is complete unless it recognizes that public psychology is part of the system. If science does not narrate its own silences, someone else will. That lesson is not about blame, it is about responsibility. Agencies must accept that communication is as vital as calibration. Third, the open end of institutional readiness. ESA spoke, NASA stayed silent, media filled the void. That divergence was systemic, not sinister. But it must be addressed. Interstellar visitors are rare, but they are no longer once in a lifetime. 3 I Divided by Atlas was the third. There will be more. Each will test our capacity to respond not just technically, but institutionally. Readiness must mean more than telescopes. It must mean pipelines, agreements, and narratives. And so we arrive at actionable promises, the heart of synthesis. If October was a stress test, December and January must be the debrief. Promises can be simple. Asterisk. To the scientific community, we will build automated first-look pipelines and schedule rehearsals for rare events. Asterisk. To agencies, we will design continuity messages and coordinate international voices. Asterisk. To the media, we will provide context early, so headlines can inform rather than inflame. Asterisk. To the public, we will respect your curiosity with honesty, even when answers are slow. This first movement of synthesis is rational, but it is not cold. It is hopeful, because every gap we faced has a corresponding fix. Every silence we suffer has a lesson that can be built into a structure. 3. I divided by Atlas may be gone, but its gift remains, a mirror showing us what to strengthen before the next test. If synthesis begins with recognizing what worked and what failed, the next step is to imagine how those lessons can be built into durable systems. A comet does not negotiate with politics. An interstellar visitor does not pause for bureaucracy. The sky gives us no extensions. To honor the lessons of 3I divided by Atlas, we must act as though the next object is already on its way, because it is. The first actionable promise is institutional readiness. Agencies cannot afford to treat rare objects as one-off surprises. They must design frameworks that live on the shelf, ready to activate at a moment's notice. That means simulation drills, continuity scripts, and cross-agency agreements that do not depend on improvisation. The October blackout revealed how fragile silence becomes when no one is tasked to speak. The promise here is structural. Never again should a government shutdown or a conjunction window erase the voice of science. The second promise is technological modernization. Data pipelines must move at the speed of public curiosity without compromising rigor. That means automation not for conclusions, but for provisional outputs. A brightness curve within 24 hours, a positional update within 48, a spectrum preview within a week. Each was flagged as preliminary, but each was enough to guide further work and reassure the public that the process is alive. The technology exists, it needs only to be prioritized. The blackout showed how damaging latency can be. The promise is to reduce that latency without abandoning care. The third promise is global coordination. ESA spoke, NASA was silent, and the contrast itself became a story. That story can be rewritten. Fast response frameworks can be international by default. Shared platforms, shared language, shared timelines. The comet did not belong to one nation, neither should its narrative. By building common protocols, agencies can present one clear message. The object is under observation. Here is what we know, here is what we do not, here is when you will hear more. This is not utopia, it is logistics. And logistics, unlike speculation, can be built. The fourth promise is public trust as infrastructure. Too often, communication is treated as public relations, an accessory to the real work. But 3I divided by Atlas proved that communication is itself infrastructure. Just as we fund telescopes and satellites, we must fund communication pipelines that translate data into clarity. That means trained communicators, pre-approved statements, and educational framing. Trust is not free. It must be engineered with the same seriousness as orbit models or sensor calibration. The final promise is embracing uncertainty as a value, not a weakness. For centuries, science has thrived on saying, "We do not yet know." The public, when guided, can accept that. What they cannot accept is silence without context. The distinction is small but critical. To say, "We do not yet know, but we will tell you when we do," is to invite the public into the process. To say nothing is to push them away. Transparency, even in uncertainty, builds credibility stronger than polished silence ever can. This second movement of synthesis is about action. It is about promises that can be made, not in the abstract, but in the operational sense. Each gap revealed by 3I divided by Atlas has a matching fix. Readiness, modernization, coordination, communication, and humility. The comet left us quickly, but the imprint it left on our systems will last if we choose to learn. The choice is ours to repeat the silence or to transform it into structure. And in that choice lies the measure of whether we have truly absorbed the lesson. If promises define direction, then the final step of synthesis is accountability. A plan without follow-through is just an aspiration. 3. I divided by Atlas left behind, not only lessons, but obligations. The way we act on those obligations will determine whether the next interstellar object is another episode of frustration or a milestone of collective progress. The first obligation belongs to scientific institutions. Researchers must commit to treating rare events not as anomalies, but as part of the normal horizon. Oumuamua in 2017 felt singular. Borisov in 2019 felt surprising. 3. I divided by Atlas in 2024 proves a pattern. More will come. That pattern demands a shift. Interstellar visitors are not freak accidents. They are a new category of recurring challenge. Institutions must plan for them with the same seriousness as planetary defense or lunar exploration. Accountability means incorporating interstellar response into budgets, staffing, and infrastructure, not as a side project, but as a standing mission. The second obligation rests with governments and policymakers. Shutdown law, funding delays, and bureaucratic bottlenecks turned October's silence into suspicion. No comet should depend on the vagaries of domestic politics for its narrative. Accountability means crafting exemptions and protocols so that basic communication and coordination survive political impasse. Governments can legislate continuity, ensuring that the voice of science remains audible even when operations pause. This is not about partisanship. It is about resilience. The third obligation lies with media ecosystems. Journalists are not villains. They operate under pressures of speed and attention, but with great reach comes great responsibility. Headlines shape perception faster than peer review can catch up. Media organizations must recognize their role not just in reporting, but in framing. Accountability here means balancing urgency with accuracy, resisting the easy pull of sensationalism when silence stretches. If science agencies provide context, media must amplify that context, not distort it. The public deserves stories that inform as much as they intrigue. The fourth obligation belongs to the public itself. Curiosity is natural, speculation inevitable, but trust is a two-way relationship. If agencies commit to clarity, the public must commit to patience. Forensic reasoning takes time. Replication takes time. Waiting is not abandonment, it is part of discovery. Accountability here means resisting the temptation to confuse gaps with secrets, to treat every anomaly as extraordinary. To believe in science is to believe in process, not just in outcome. And finally, the obligation belongs to all of us collectively. Because 3I divided by Atlas was not a national object, nor a private discovery. It was a messenger from beyond, shared by humanity. Our response, fragmented, delayed, mistrusted, was a rehearsal for larger tests to come. Asteroids, comets, cosmic anomalies. The sky will continue to deliver them. Our systems must rise to meet them, not stumble in their shadow. So the synthesis closes with open ends, but hopeful ones. We cannot rewrite October 2024, but we can promise that October 2026 or 2030, or whenever the next interstellar traveler appears, will be different. We can promise that silence will be scheduled, not suspicious, that data will flow provisionally, not be trapped, that voices will be aligned, not divergent. Above all, we can promise that trust will be built deliberately, transparently, and patiently. The comet has gone, but its legacy remains. 3I divided by Atlas was not extraordinary in physics, but it was extraordinary in what it revealed about us. The final promise is that we will learn, we will build, we will prepare, and when the next visitor crosses our sky, we will greet it not with doubt, but with readiness, clarity, and a trust stronger than silence.